to 7 meters a tunnel is passing through. So problems are too many. So we need to assess whether the tunnel is going to stand or the structures above the tunnel on the surface are going to stand or not. So these are the issues wherein we need to divert little attention and then do something. And this is again continuation of the same I am showing. Yeah, this is a large cavern which I have mentioned. You can see the height of this. A fellow is standing here. Designing, we don't have any expertise in the country. Lot of work is going on. Large number of projects are being taken up by ISPRL, Indian Strategic Petroleum Reserves Limited. It is a consortium of all oil companies coming together. Huge money is involved. And this is a storage facility we have in Bangalore. You can find approach roads to the caverns here and here. Without numerical modeling, nothing can work in civil engineering designs nowadays. So I expect my civil engineering colleagues in GITAM and mechanical also now divert towards research in taking up the projects using numerical modeling approach. Every project, every consultant in India is using numerical modeling for designing the structures. You can find that some 3D keys there. This is the most advanced version of distinct element modeling software. I think NRM is having, and then we at NIT Surathkal got it. I think more than dozen MTech projects were produced and 3 PhDs or so were produced on this. NRM continuously uses it, and they generate crores of rupees consultancy, crores of rupees worth consultancy. And here you are finding a small instrument. Lot more will be talked about these instruments by Professor Dr. Venkatesh. These are ground vibration monitors. I think we have already placed an order in a week or so. We are going to get 2 units to GITAM as well. And everywhere you find in Hyderabad also, lot of construction activity you have. And excavation work is going on adjacent to so many developed colonies, developed structures. And you are dealing with hard rock. When you deal with hard rock, it requires blasting. When you conduct a blast, it generates vibrations, noise, rock pieces flying. How to control? So stability of the structures or protecting the structures from ground vibrations generated is a big area of work with huge consultancy potential. We have been working on that for last almost 3 decades plus. And now another area is how much energy is going to be generated by these vibrations. Can some energy be generated and stored to run your computer systems at least in the organization from the vibrations? We are working on that based on piezogen based this electric generation, power generation. The next one is high speed videography, because when you talk about a blast, everything happens in a fraction of a second. Everything happens in a fraction of a second. But everything also happens within that fraction of a second, and that may be good, that may be bad. For your information, I will just give one example. In some of the mining projects in Northern India, Northern Coalfields Limited, one single blast, you see in movies, no? In the climax, villain wants to blast the structure or factory of the hero, and somehow hero does all the fighting, and at the end of the day he stops the blast. With the press of the button of that exploder, you are going to execute a small amount of plus 1.5 crores only. And the bill of explosives of Coal India Limited alone, one organization, exceeds 10,000 crores a year. So much is the scope of work. We don't have people. If you, in every civil engineering project involving rock, requires blasting. And if we talk about blasting, as on today, I can't take more than half a dozen. Professor Venkat and Dr. Venkatesh. Dr. Venkatesh is 1, Shastri is 2, VMSR Murthy 3, Mishra 4, Director Sim for Dhanbad, Ramlu 5, now my Sisha, another Sisha Ramchandar 6, then maybe 2-3 more are there. In this entire nation, which is going to execute projects worth of lakhs of crores of rupees. Tremendous potential for consulting. You can start your own startup. You can have your own startup in consultancy of blasting, sitting in Hyderabad. And for your information, 60% of construction projects, you name any sector, are being executed by the contractors sitting in Hyderabad, construction companies sitting in Hyderabad. So much is the scope for you guys. 60% of infrastructure projects in the country are being constructed or executed by companies sitting in Hyderabad. You can think of. Now, with this high-speed camera, it can take 1000 frames per second. 1000 frames it can take per second. Therefore, you can analyze many things. At the end, I will show one film and close. This is how a blast looks like. You might have seen in some movies like, I don't know, recently, Balakrishna movie was there. In that, it was one blast was shown, Akhanda. And prior to that, Rana movie was there. In that also, they have shown in Iron Ore Mine, I think. So one blast, something like that. But and this is something about our Namma Metro, Bangalore Metro. This is the plan, connecting so many stations. Coming to this excavation, you are finding some excavation, and this building is the most prestigious organization sits in this building. This is Hindustan Aeronautics Limited building. On one side you have Aeronautics HAL building. On the other side you have GPO, General Post Office, constructed by Britishers, which is declared as Heritage Center, masonry structure. And excavation was done to construct underground metro station. And you are finding this all soil. So civil engineers will have to protect this slope. If you don't protect, HAL building is going to collapse. But if you go and see now Bangalore, HAL, that is Cricket Stadium or Vidhan Saudar, Majestic stations, you find beautifully those things are developed. And one more piece information I would like to share with you is, all the metro stations in Bangalore, you find a different design. No two stations will be of similar structure, similar design. And the general architecture, how it should look like outwardly, was designed by students from engineering colleges in Bangalore. And BMRCL has floated a competition, and students have given the design. Outward, how it looks like. So that is where we are progressing, how we are progressing in the country. And the excavation was done. I think we were consultants, and NRM also was consultant. You can see we have gone up to almost 30 meters below this structure, and you find hard rock to be excavated by blasting only. Around 15,000 plus blasts were conducted for 5 years of time. On not a single day any adverse report came in any newspaper. That's how so meticulously it was executed, wherein lots of inputs have to come from different disciplines of engineering. And this is GPO I was mentioning about. So you find so many structures here, and excavation was done to some extent by directly digging, and to a large extent by blasting, without disturbing these structures. But in Hyderabad, I see everywhere they use hydraulic rock breakers to do this excavation of hard rock, and the project goes on for longer period of time. Another thing is metro. We all feel that if you do blasting, then it is going to disturb the structures. But no one has thought of that a moving metro train is going to generate some vibrations which may disturb shops and houses and other establishments. For the first time, this study was taken up by BMRCL in Bangalore to protect the structures of CMTI. I think professors of mechanical engineering may be knowing this organization, Central Manufacturing Technology Institute, where instruments concerning nanotechnology based instruments are manufactured. It is only one of its type in the country. one of 6 such facilities in the world, and very, very sensitive labs they have, and they don't allow people to walk, only one person is allowed without shoe, and that entire lab is almost, it is a hanging sort of thing, it is not grounded to the earth, they have some mechanism. So sensitive structure it is. So they have gone into the studies related to the vibrations generated by moving metros. Nobody in India thought of. We are moving, and the CMTA engaged professor from Buffalo University, USA. And Munnar, every one of you know for something, but Munnar holds one of the toughest hydroelectric power project, wherein this maintenance of the slope is a big problem. NIRM was involved. 3 times they had to change the direction of the tunnel. Almost 600-700 crores has gone under the drain. Root cause, we don't have really expertise to deal with the problem. So friends, numerical molding, these are some of the problems. And then when you come to port sector, all the ports are going for tremendous expansion, deepening of the ports. If you have the depth of water more, then you can invite large capacity ships. One of the pet projects of present government is expand the ports. When you go for expansion, you have to excavate the material. If you encounter rock mass, you have to blast, and we blast from a distance of 2 to 3 meters. Below this, there are piles supporting the structure. So 2 to 3 meters from the structure, blasting has to be done, protecting the structure, which is worth of around 350 crores roughly. One structure will be. So stakes are too high. We don't have experts. Some 2-3 experts are there in the country. Many other things are involved in this. So these are some of the pictures I am showing. So, and in refineries, lot of expansion is there. Again, rock excavation, rock engineering. You need to blast without causing any damage to the existing facilities, and then canal works, many canals collapse. So these are all the issues you have, wherein good amount of knowledge needs to be developed by you people. Thank you very much. I think you will start thinking something about these things. I pass on the podium to Dr. Venkatesh next. Thank you.
I deem it my privilege to introduce our chief guest, Dr. H.S. Venkatesh, Director, National Institute of Rock Mechanics. Dr. H.S. Venkatesh is a graduate in mining engineering from Osmania University with post-graduation from IT, BHU and doctorate from NIT Surathkal. Dr. Venkatesh joined NIRM in the year 1990 in Rock Blasting and Excavation Engineering Department as Scientist B and is currently the director of the institute. He is well versed with open cast and underground blasting operations and is an established authority in the controlled blasting technique. He has authored over 70 papers and completed about 200 industry-sponsored as well as R&D projects at NIRM. Dr. Venkatesh is a recipient of the prestigious National Mineral Award, Government of India for the year 2004 in Mining Technology, Distinguished Alumni Award of NITK Mining Department for the year 2003. He is a Fellow of the Institution of Engineers, Vice President, International Society for Rock Mechanics, India, Vice Chairman, MEAI Bangalore Chapter, Member, International Society of Explosives Engineers, and a member in several professional bodies like ITA, ISRMTT, MGMI, ISEG, etc. He has visited Australia, Singapore, Bhutan, and USA. He has been in committees constituted by the Ministry of Mines, MOEF and CC, Government of India, the State Government of Andhra Pradesh, Telangana, Uttarakhand, and Karnataka. He was a member of R&D Board of Coal India and is a member of PERC, SSAG, Granite, and Marble Development Council, GOI committees on dimensional stones. Now, I request Dr. H.S. Venkatesh, Director, NIRM, to present his talk on rock blasting, a tool for development. Thank you.
Thank you, ma'am. And you can play iron or a. I'll just show a couple of blasts to. This blast was in an iron ore mine, and then I will show you a blast for. For urban environment in Bangalore Metro. This is called controlled blasting. Split. Idi. This is at a nuclear project in Rawatbata, Rajasthan. This is a specialized blasting called pre-splitting. Result of the pre-split. Now the blast, what I said, pre-split blasting, there is nothing like, you need not see any rock movement or anything, but this is how it has generated a crack within this. I will show you the result. The blast what you have seen, I will show you in my lecture. That means it is only creating a vertical face without damaging any rock mass, so that we have 15-20 meters of vertical face. So this is a specialized blasting. This is how a crack has been created. Even the blast hole has not been damaged. So this is one form of controlled blasting. So rock blasting, I will take up to 12-15 probably, another half an hour to 35 minutes. And rock blasting a tool for development. Now what do we mean by development? Development is something which can create a resource for the sustainability of the nation or an individual. Now here if we look that, I have shown you the Chennai airport. The Indigo aircraft what is standing is at the Chennai airport. This is probably 1.5 years back. And the adjacent building what you see is that we have done the blasting, control blasting. And then this is the terminal 2. And probably some 3 months back or so, it was inaugurated by our Honorable Prime Minister. That means airports are constructed, your travels are enabled when we do excavations, and excavations are done through hardcore blasting. Now, why do we need blasting as a matter of fact? If you look at this slide, caveman to modern metro man, caveman, roti kapda, khatam, that's the end of the story. When we have food and clothing, and then caveman was very comfortable. But the need, the urge, the greed of an individual to have a comfortable living needed shelter, and it did not end with that. With the shelter, the mobile has spoiled our life. The shelter, we are confined to our rooms and spoiled our life. So with this roti, kapda and the makan ke piche chalte, everybody after me and Professor Shastri that ki chalo yaar create karo, usko sustain karne ke liye. Now what sustains society or the nation, broadly I have put it for you, is that mining, agriculture. What cannot be grown has to be mined. So what cannot be grown has to be mined. So mining sustains the society, and to sustain the mining, to build the nation, enable you people to make your software. Those people are in the computer science or electronics, to make the tools, ADAS devices, to put on your car which is made of metal, is what sustains the society. Health, education, knowledge, information and data. Today education is the last one, data is the first one. The priority of every individual is analysis and handling of the data. What kind of data is of no relevance to us? Infrastructure and energy. This gives us Shiva move kaatleeda. You have seen a lot of slides shown by Shastri Saab. Now, blasting is required in underground mines, open cast mines, tunnels, caverns, canals, hydel projects, construction industries, then riprap blasting for breakwaters, metro, urban blasting. So every of these, how do you use these tunnels is your wisdom. You run a train, you run a train, or you use as a water conducting system. It's for a tunnel, whatever it is, you need to excavate it, and then we need blasting. Now these sectors are directly dependent on what? The mining sector, energy sector and infrastructure sector. All those which I have to listed needs, and when we do this, the nation builds. So for the development of the nation, what we need is to generate a mineral, may it be coal, may it be limestone, may it be iron ore, that is one part, or create a cavern or a tunnel wherein you house your equipment, you store your crude. For all these things, the fastest, easiest, cheapest way of doing is excavation by blasting. Now, I will just come into the technicality of it. I don't want to, because I have got an amalgamation of students of various backgrounds. So, I will limit it to certain extent that whenever we want to choose a method, like how if you want to choose a tool, the compressive strength of a rock mass is one parameter that we generally consider the cuttability or the blastability of a rock mass. Leave behind the properties of the explosives. So if you look at drilling and blasting from almost weakest rock, maybe 5 MPa, which we can call it as soil, almost soil, 5 MPa, up to 130, 140 MPa, 140 MPa to 200 MPa, drilling and blasting is the only versatile tool for excavation of the weakest to the strongest rock. Now, if you want to use any machine, call it tunnel boring machine, you can see it is almost that you cannot work in weaker rocks. If you go to Himalayas, in the papers, if you read it, the tunnels, they have got stuck because of the tunnel boring machine, because the rock mass is weak and TBMs are not capable of handling this kind of situations. Road headers, and this is for the soft ground shield, this is for the mining engineers understand. Whenever I go for blasting, what are the issues I have to face in the society? One is the regulators and the safety people. They say blasting mat karo yaar, risk hai. We have to convince them. Now the next is administration, forest people. My animals are there, my snake is there, you are disturbing them. So the environmentalists say that ki blasting nahi chahiye yaar. Then you go to archaeology, say this is a heritage structure, it is almost 1,000 years old. Now, so, no, we don't need blasting. Now, there are enforcement officials, explosive act, this act, those people, whether you have got permission to do this, do that. Then stakeholders, public, they say that my building get cracked, I have a disturbance, noise, these things. So they say that we don't want blasting. Then legal petitioner, there are so many NGT cases, court cases, we get summons. So they say that no, this is the worst part, you are spoiling the society. But let me tell you, with all these things, I will show you a couple of slides where we have successfully executed. But for blasting, nothing is required. Any of you can do blasting, because if you have got a blast hole drilled in a design pattern, put some explosive and then connect it to a detonator, it blasts. It doesn't require any knowledge more than that. So these are the three requirements. You need to have a blast hole, you put an explosive, you need an initiator to trigger it. Once having got these three things, what just small things you have to look is that what is the distance that you have to keep that blast hole away from that is called the burden, spacing and the bench height. These are the terminologies, I am not going to put it. So this is called the design aspect of the blasting. Now for this is a mining slide. The entire blasting has been put in these 4 slides, that if you have a blast hole, you can have a blast hole diameter of 38 mm up to 311 mm. If you imagine a 311 mm blast hole, the explosive that can go into a single hole of a 40-meter bench will be almost around 1.4 tons of explosives can go in a single hole. And if you are blasting almost around 100 holes, it can be more than 200 tons of explosives at a single time. So this is the size of blasting that we handle in India in the mines, and in a small project, how you have seen in Bangalore Metro, that is all 38 mm diameter, we are using 1 kg, 2 kg explosives. And I will not explain more into this. I don't know, online audience, if there are mining, they will miss it. When you do blasting, what are the issues that they come out? The issues that they come out is design issues, that people will say that the cost of blasting is high, that is economic issue. The other one is technical issue. We are having huge boulders which are not be able to be amenable to be further used down the line. That is one part of the technical. What is the other issue? The adverse impacts. Whenever we do blasting, one is techno, economic, social, environmental, legal. This is where we spend lot of our time in convincing when we do the blasting. Now this is once again, when I say the blast design issues, there are set parameters governed which we have to look at. That is the burden distance. The first this is what you can see. This is what burden. I have taken an average of many parameters. Keep it in this. The burden looks, when you increase the burden, the spacing distance, the adjacent hole increases. But something called burden to blast hole diameter, almost it is constant. Because of that, what is happening? The explosive which you are putting is getting down low, so you are going to have environmental issues. This is the zone where we are going to get the designs in this. I will not elaborate on that. What are the environmental issues that you are going to face? The environmental issues you are going to face is the ground vibration, that is the vibration that you feel. The air over pressure is the noise that you are going to hear, the air concussion in the blasting, what you have seen, heard when we showed the video. Environmental issues many times here is that the dust, which people complain, my agricultural land is looking white or black because of limestone or the coal dust, or because of the excavations, the water table sometimes may come down. These are certain environmental issues, social issues and the legal issues. How do you tackle this? Like all you have the computers, we too have the computers, we too have the tools, we too have the electronic engineers working on this. These are the gamut of instruments that we use it. Now, I have shown the entire systems of the tools which we use. We understand the rock mass by having the sonic velocity of whether the rock or the concrete. we have the modeling softwares, we have the distance measuring units, we have the high speed camera, we have the fragmentation analysis tool, we have the vibration analysis tool, we have got the explosive analysis tool, we have got the air or pressure monitoring systems, we do have the empirical and the numerical equations to come out. We have got borehole cameras to see what exactly the crack propagation is that. We have got three-dimensional analysis, and then we use drone to completely capture in real time the blasting. So it is a matured engineering field. Rock blasting is not something I said that you put an explosive in a hole, connect it and blast it. This all goes behind this to come out with a successful blast design. Now this is how we monitor it's a hardcore blue collar job. It's not a white collar job. You have to be at the field. You have to take a lot of dust and heat and the hard helmet area. Now I'll show you the learnings. The videos have just put it for you that key when you see this, you are seeing the flying fragments everywhere. Now if somebody does a blast, there are 3 holes you are looking at. There are 2 systems, something called the detonating card we are using for the initiation. The other one is we are using angular chips and the drill cuttings with the detonating card. This blast looks very clumsy. That means if somebody is close by 200 meters, 300 meters, you see there are flying fragments that are going to land on your head or in your vehicle or in your house. Now how do we go out? We go out with an improvised technology, what we call shock tube systems. Here the conventional drill cuttings are used. Here we use an angular chip. So this is a research work what we have done. And finally you can see that one hole is getting ejected. Rest of the holes you don't see a flying fragment. This is an ideal blast. I have not muffled it. I have not put any rubber mats. Earlier you have seen in Bangalore Metro, you have seen a rubber mat to hold the rock mass. Here in the design itself you can see by using the proper design you can blast. There is no flying fragment at all. So there is something called the stemming length, stemming material and the initiation system. These are the technical things which we go about and then design a blast. And then let me tell you here, if you see it for a layman also, if you see the blast hole diameter here it is shown 150 mm and the other one, the triangular one is showing 110 mm. Conventionally, you might be thinking, logically reasoning is that the smaller the hole diameter, the flying fragment will be at a shorter distance. But let me see here, in the experiment, 150 mm has given lower fragmentation, lower flying distance, and 110 mm smaller diameter has thrown the fragment far away. So this is paradoxical. You can feel that higher the charge. The thing is that when the charge is smaller, you are having smaller bench height. The smaller bench height leads to larger flying distance. So this is an experiment done for the Chennai Metro. Chennai Metro, I took the help of some of the electronic engineers there, and when you see a Bangalore Metro or a Chennai Metro, there is something called, civil engineers will understand, top-down and bottom-up method. Top-down method, when you call it that, when you make an excavation, you excavate the top, then put a concrete, have some small holes in between, then go down in that. In the top on the concrete, your traffic will be going on. Under the canopy of concrete, we will do the blasting and keep going down. That is called the top-down. Bottom-up is what you have seen in Bangalore Metro. Everything is open. We excavated openly, went to the bottom and constructed the columns and then made the roof. So in the bottom-up method, what is the problem? You cannot use the road for almost 2 years, 3 years. So top-down method, generally it is used in soil strata, but unfortunately for Chennai Metro, they landed with hard rock in some of the stations. So we need to blasting. Now when you do blasting, we do not have a data to say that I am doing blasting in this room, what happens to the concussion force, because a lot of gases went out and it exerts pressure onto the roof. So for when you have made an artificial canopy, it may get lifted. So we conducted specialized experiments, constructed a concrete canopy, and then we have put a pressure cell, mounted a pressure cell, if you are seeing it. And then this is the cell, dynamic pressure cell. It is costing almost around 15 lakhs because in real time, it's in microseconds. It's less than 300, 400 microseconds, that is the entire action is taken place. So it has to capture the data, and the data set should be almost in terms of almost around 1 lakh to 2 lakh data sets has to be taken in less than that. So we should have a high precision pressure cell. It's a pressure transducer. So we customized it, got it, and then did the experiments. Now this is the Bangalore Metro. Now you can see in the nation building, when I say that you excavate this, you have seen this. This is the Vidhan Saudha, and today this is what it is. Yesterday it was that. Today it is the metro station. Below you are going down into these areas which we have excavated and created space for your train to move. Now, how did we do the blasting there? Lessons to be learned. Shastri Sahib said that heritage structure is there. Heritage structure is there, and we blasted very close to general GPO and this thing. How it did happen? This graph says us. Now, when I said that the effect of vibration is there, there are certain standards we need to. When you do a blasting, we generate a calculated intensity of vibration. We say that what is the permissible limit, our design will incorporate, and it will not generate more than that intensity of vibration. So that we call it charge per delay, which we control and we use it. Because of using this, the red zone is that from 0 to 20 meters, if you can see the measurements, from almost 5 mm to 50 mm, the vibration can vary. Then we will not be in a position to take any risk. Because if you put the same charge, the graph you can read, it can be 5 mm or it can be 50 mm. This is the phenomenon of rock mass behavior in near field. Now, once we are going beyond 20 meters, you can see most of the data sets are very close to the x-axis. That means that whatever explosive you are putting, it can be less than 10 mm. So we said that all blasting to be done beyond 20 meters, and that's how the metros are. So this is the basic data. Based on this, the designs have been evolved for the urban blasting. Now, this is at the Gulbarga Cements. There is a 1320 megawatt power project in Gulbarga, but a limestone mine want to start their own limestone cement manufacturing. So they had a lease, but the people, PCKL people say that I don't permit, because when you do blasting for limestone mining, then what is going to happen? My switch yards, they are going to get tripped. There will be a problem on that. So they did not give permission. So the solution to this is that we also did not do any blasting. We took the data mining. We took all the data what we had and whatever data is available elsewhere, and then put it in this and fitted the best fit line at the 90-95% confidence level, and back calculated what should be the permissible limit on the worst case scenario, and said that these designs we are going to use it, and the permissions. So the limestone mine started working. Now this is Hyderabad. This is Hyderabad, and this is blasting in Film City. The building what you are seeing here is Ramanaidu Studio. This is Ramanaidu Studio, and this is all excavated due to blasting. We are doing by blasting very close to Ramanaidu Studio. This blasting has been happening for the past 1 year, and these are the expensive, what you call it, flats that are going to come. Probably our computer software engineers can afford, not a mining engineer. So not a mining engineer. So these are the buildings that is come. This is called the urban blasting. Had they done with mechanical excavation, this would have taken almost 4 to 5 years, but we have completed in 8 months. So this is what is the power of blasting. This Tungabhadra Dam, almost 1910, and then we need power. How do we generate power when water is there behind the dam? So we say that we have to set up a power station. We do drilling and blasting, and then this is what you see. The previous figure is this one. We have excavated the entire, very proximity to the 100-year-old concrete dam, and then this is the mini powerhouse. This is how after the construction. This is in Bhutan. It is a 1320 megawatt Thala hydroelectric project. The cavern, what you saw, Shastri Saab showed, was that the orangish one, the big cavern, is from the Thala hydroelectric project. And then this is the dam of Thala hydroelectric project. They wanted to augment 25 megawatt more. Each megawatt of power to generate today is almost, it comes to around 7 crores per megawatt. So if you have to generate 25 megawatt, it is almost around 25 into 7, around 200. But 25 crores we spent, and then another 25 megawatt of power has been augmented by making a tunnel on the abutment of the dam itself. This is the dam abutment. On the abutment of the concrete dam, we have done controlled blasting. This is the Punasangsho hydroelectric project in Bhutan. There was a huge fall, almost 190 meters, and almost 2 lakh meter cube of rock mass has collapsed. Now there is no access to this. We have created an access from the top, from an alternative route, and then completed the project. And Dr. Shivaprasad has, I don't know whether you share that information there or not, he has come out with an indigenous system of having sensors mounted, 9 sensors I think, he has mounted into this rock mass and then buried into this and backfilled with concrete and then monitored the deformations. Even now the data is coming. So this is what we at NIRM do and what rock mechanics does to the society. This is how we map the entire mines, and then we can mount on this any sensor, damn it. Any sensor, an electronic engineer, if you put a thermal sensor on top of it, you plan it, map it. The only thing is that you should have a tool to analyze the data. You should have the tool to analyze the data. Now, why I am sharing with you is that I expect from you people, recently I attended a Startup India program at IIT Bombay. That was the initiative taken by our Ministry of Mines. Secretary Mines and the Minister Mines was very keen that there should be startup in mining sector. Let me tell you, in 2004, the Startup India movement started. Until 2015, there were only 100 startups. 2015 or 16. Today we have got 1 lakh startups. Today we have 1 lakh startups in India, more than 100 unicorns here. But there are only 82 startups in mining. Why I am saying is that there is a huge scope for you, dream big. If you read the paper, you say that in Uttarakhand, in Himachal, if you see Kulu is cut off. There's a huge opportunity for the data scientists here that if I have a tool to analyze in real time, that what is going to happen, because next year also Bias and Sutlej is going to flow. But today, if you are able to understand the movement of water and say that one day before I will tell you that the water level is going to increase by 1 meter, 2 meter, 3 meters. You tell me, there is a huge scope for you. There are startups that you can come out. What all I am showing is that these data have to be handled by you electronics and computer scientists. We will put the hard hat and then work there, but you will analyze the data for the future. Prediction is in your hands. That's what I'm saying. In India, predictive tools, analysis tools are minimal. All the softwares which I am telling, rock mechanics softwares are imported. We are paying through our nose. All the softwares what we are working on, finite element or the discrete element code, we buy it. But why can't our young friends? There is no rocket science in this. This is mathematics. Math involved in that, you can program it and then in real time people can. So there is a huge scope for you to enable yourself to be an entrepreneur. That's in rock mechanics and rock engineering. Now this is typical how we can, in a mundane routine life, how we can innovate ourselves. A big surge shaft. For power generation, we need to have a surge shaft. This is a surge shaft in Bhutan. It got clogged in between. If you are seeing is that this is a 16 meter diameter, there is a 3 meter pilot hole here. It is clogged. Now there is no access for that. What to do? Then we thought that this is, I am talking about 2002. What we said that can't we think of pop shooting? Pop shooting means that you place an explosive abutting the choke, it will blast and it will fall down. But it's a risky. You have to climb in a 3-meter rock. We don't know what is going to come on your head, but who will take the risk? Then we said projectile charge. Why can't we think like army people, when they project it, it can hit it. So we can devise a projectile charge. We thought it. The other one is drilling from the shaft bottom. The other one creating a new axis. So this is how we constructed a pop shooting tool. It's an indigenous pop shooting tool where we fixed up into 1 inch, 3 inch pipes and then moved it almost around 27 meters. And it failed. We did not, like how Dr. Venkatrama has said, we never fear from the failures. We make it a learning. We said that, okay, this pop shooting has failed. Let us attempt on projectile. So there is something called in blasting where you have a charge, a shaped charge. If you are going to put a material in this V angle and then put an explosive below, then what happens? The energy is concentrating at a distance away. So this is called shaped charge. This is generally used for seismic studies. So this shaped charges, it has got a depth of around 3 meters, 4 meters. So what we said, we tried to create a shaped charge and then push a platform so that it hits. It did not work. Then we decided there is some drainage gallery like a tunnel access. From that you drill 100 meters and then address the tackle, because the entire power project 5,000 crores rests on opening this choke, or else the project will be then that also was a difficult proposition. Then finally what we did was, we identified an intermediate location, made a tunnel of 25 meters, directly went at the choke and then put the explosive and blasted. Now this is something called, there is a heritage temple, Kumaraswamy temple in near Bellary, Hospet. Iron ore mines are there. Iron ore is a resource. We have to judiciously use it. There is temple. So there is a Supreme Court, there was a Supreme Court judgment that within 2 kilometers of the temple, no blasting to be permitted. We said that it's a national resource. If we can protect the temple from the blasting, what is the problem? So we conducted experiments, and then today permission has been given up to 600 meters of the heritage temple, which is 1,000 years old. The temple is now safe and the mining is going on. This is how the data sets, I will move through this. This is at the Rawatbhatta, Rajasthan nuclear power project. I am running through these slides. Now, this is how we use the excavations. This is the excavation you have seen. The end usage in nuclear project is this. This is the conducting systems which are going to be housed there. So you do this excavation, this is the end product you see. The blasting which I showed, pre-split blasting, this is the split it has created, this is the thing. This is what is the end result. This is what is called the pre-split. This is almost 15 meters. 15 meters. We did almost 8 months before. So what is that we have done? We have maintained the integrity of rock mass. So we have not damaged the rock mass. We have given a vertical face to the rock mass. You can construct. This is the pre-split. The advantage with this is that if you are having an angle of 70 degrees, the extra rock mass which have to be excavated will be almost around 8 lakh meter cube. Where do you dump it? Where do you dump it, that extra? So to give a vertical face, you need to have a specialized blasting technique. Pre-split, this is what it is that. When you do that, this is one more experiment that this is in Karnataka's what you call near Hospet. There is a railway track going on top, and then underground you need to make a tunnel. The cover is almost 14 to 17 meters. Now this almost 6 to 7 hours traffic jam was there. There was no solution. Railway people say we don't permit tunneling because our active railway line is going on, and the government was not interested to construct a flyover. Now this is a logjam. Then we convinced the railway people and said that we will do tunneling below this and we will not generate the vibration intensity more than what the trains generate. Train is also generating vibration. Then with the train generation you are permitting, blasting why are you not permitting? So they said, how do you do that? We said we will monitor the train vibrations. We have mounted the sensors and we monitored for almost a week and created huge data sets and said that what is the maximum intensity of vibration the trains generate, and the ground vibrations produced by train has been 58.4 mm, 68 mm, 60.8 mm, 50.6 mm, 57 mm. We said that with blasting we will not exceed 40 mm. Yes, done. After that, every blast we used to monitor the level on the top. That is there any subsidence sinking because of the excavation below? Because it is a shallow depth, 14 meters is too shallow condition. We have all the data. If you are saying it is 0.005 mm, this is the tolerance levels at which we have. Then if you are saying the RL, it is 57.165 meters. In that 0.005 mm is the tolerance limit at which we are working. And the deformation measurements in the tunnel we have monitored. And finally, this is the blasting methodology we have used. Stage 1, that is the heading, side slashing, and then benching. These are the blast designs what we have used. These are the delay intervals that what we have given, delay number 1, 2, 3, for long delay we have used. The charge per hole and the total charge is given. The cut holes, spreader holes, stoopers, floor holes, and final, this is how it started. This is how it has progressed under the railway line, and today this is how the tunnel is completed. This is how the tunnel is completed. I think Dr. Jha, I said 12:15. I rushed the slides, and thank you.
Thank you so much, sir, for briefing our participants with the concepts of rock blasting. Now I request Professor V.R. Shastri, Director, GITAM School of Technology, to present the memento to our today's chief guest, Dr. H.S. Venkatesh, Director, NIRM. I request Professor T. Madhavi, convener of this workshop, to join him. Introduction of our esteemed guest, Dr. P.C. Jha, Scientist and Head Engineering, Geophysics Department, National Institute of Rock Mechanics, Bangalore, by Ms. Priyanka.
Thank you, ma'am. I deem it my privilege to introduce Dr. P.C. Jha. Dr. P.C. Jha is a geophysicist with the postgraduate and doctorate degree in applied geophysics from ISM, now IIT Dhanbad. He joined NIRM in 1990 in the then seismology department. From 1990 to 96, he was working in the field of mining induced seismicity, MIS. He established the engineering geophysics department at NIRM in 1996. His areas of specialization include, amongst others, microseismic monitoring, defect mapping and characterization, foundation evaluation for buildings and structures, stability analysis, substance studies, vibration data analysis for damage indices, both active and passive, and forensic investigations for critical failures. Dr. P.C. Jha has guided for five doctoral thesis work from IITs, ISM, NIT, and VHU. He has authored over 60 papers, edited and published 2 conference proceedings, national and international, and completed over 120 research and industry sponsored projects, including SNT projects and international collaboration project with NGI Norway. He is a life member of several professional bodies and scientific societies in the field of geophysics, geology, seismology, IT, NDT, and rock mechanics. Thank you. And I will now request Dr. P.C. Jha to deliver the lecture. Thank you, sir.
Thank you. Thank you, madam, for a nice introduction. Today, I will be talking about this ground penetrating radar. I think it's a well-known instrument to our present day society. People are very much fascinated when it came to use of radar, and it is now omnipresent. Everywhere we go, there is a GPR, and people have procured it. So where it lacks and what is the advantage, I will just brief about it. We have some case studies. We have so many case studies here. So I will just go ahead with my presentation today. So how do we define this GPR? Essentially, it is a non-invasive sensing technique based on electromagnetic methods. And it is effectively used for subsurface investigation, 2D and 3D imaging, and diagnostics affecting the entire gamut of civil engineering works. So when we see this radar, there is a word called DAR, that is detection and ranging. So all radars are basically detection and ranging. We have many varieties. Like radar, when we say it is this is radio waves using detection and ranging. LIDAR, it is light wave using detection and ranging. SODAR, we have sound waves. Each is used for its own purpose. When we say radar, it is distance, speed, angle of motion, flying targets. LIDAR we are using for remote sensing tools, DTM, mining, forestry, power line, transportation. SODAR we are using for wind profiling by scattering of sonic waves, atmospheric turbulence, etc. We use SODAR here. So like any other radar, GPR also is a detection and ranging tool. But unlike any other radar, its operation is a little bit complicated. Why I am say complicated? Because in all other radar, whatever we see, the medium is constant and we are mapping only target. But in this case, the medium itself is varying. The ground is never uniform and it's homogeneous at one place. Today it is one type, it has rained yesterday night, whole night today, now also it is raining. What we have got data yesterday with GPR, it will not be same today. The question here is, when medium is such a thing changing, what we can detect? The anomaly is introduced by the medium itself. And now we are going to detect the target. That's why it makes it a complicated thing. But despite all these complications, we have to use it because it is a tool. So in geophysics, GPR is essentially an electromagnetic tool of investigations. And like any other electromagnetic tools, it has also a source, that is a transmitter, which is an antenna. Then we have a receiver, which will be frequency tuned coupled electromagnetic antenna pair. And we have a data recorder, which is essentially a PC, which records the strength of the signal, normalized strength, time delay over transmitted signal of the signal reflected by the target. So we are sending a signal, we are recording it back. So what is the delay between the recorded signal and the sent signal? We are recording the delay. What is the loss of the amplitude between sent signal and recorded signal? We are recording as a normalized output. So these two things we are recording, and based on that we are doing the entire interpretation. So where is the complication? So it is all introduced by the ground, as I explained. So what happens? The ground distorts and modifies the incident signal, because while reflecting it, it makes the target blurred because the ground is changing. Then there are some type of grounds like shale or clay which absorbs the signal, and then there is nothing reflects. So it becomes an opaque. So we cannot work with GPR. we will say GPR has failed, target is not detected. There are sub-targets like RCC, metal sheets, which absorb GPR signal, and there also target becomes opaque. So these are the problems we face when we do in the field. And how we overcome that, I will discuss it here. Then second problem comes, source signature of man-made structure is not known to identify the defects. This explains that whenever we are mapping a defect, like a doctor goes, you go to a doctor and takes an X-ray, he will say bone is fractured, because we know how the intact bone looks like. But when we do a GPR survey, we don't know how the intact signature will come. So based on the GPR signal, if we want to identify the crack or damage, we must know how it was looking intact. If that is not known, then it becomes difficult to identify the defect. Then considerable expertise is necessary to effectively design and conduct a GPR survey. It's not plug and play system. We go and do some survey and come back. All noise will come. Then third thing is interpretation of GPR section, that is radargram, is generally non-intuitive. That means it requires a specific competence to enable GPR data to be transformed into clear pictures for enabling engineering decision. So all signals do not transform into output, and all output do not transform into engineering decision. So for making engineering decision, you need a lot of competence. While collecting data itself, you should have proper data. We can't come back with a noisy data and say that it has not worked, or we will give some blurred image. Then today the fashion has come, everything is software dependent. Software interprets and gives me the answer. Now the plug and play GPR has come. That is totally misleading. We have seen many sections which does not give any answer with software dependent GPR. So these are some of the problems which we face here in GPR handling. I will explain one by one. Then there are other complications, like there are echoes. If you want to use in this hall GPR, as you know, radio waves are not attenuated in the air. So I am looking at the subsurface, but it will come 20 times from the roof. It will come down and go back, come down, go back. So multiple echoes will come. So these creates the noise which dominate the signal, and we do not see anything subsurface. Then localized feature also. Some localized feature is not coming as a true image. It will come as a hyperbole. When we traverse the area, as we approach the target, there will be a good signal, and as we go away, it will fall down. So we call it a hyperbole. Then depth of scan varies from place to place. In this campus, we may get 5 meters because it has rained yesterday. But if we go to a next 10 meter away where it has not rained, it will be able to scan up to 30 meter. So we can't say with this equipment my radar works 30 meter. It depends on the condition. So it varies from place to place. We do not know beforehand. We will come back with an antenna and start scanning, then it is not going. So that is the problem we have to tackle first. Then if we want to increase depth, we have to lower the frequency. If for lowering the frequency, we have to change the antenna, or we have to increase the power expense. There are many factors. So there is no thumb rule applies where we can increase the radar range. So therefore, very often what happens when we go as a plug and play system, the GPR fails to meet the objective, and we come back, we say GPR does not work. I have seen many cases. I have been presentation, people purchase GPR, but they say it is not working, I have kept it aside. So why they have kept it aside, we will come to know later. So what are the elements of GPR? As I said, we have a high frequency radio waves, which is 1 to 3 gigahertz. Sometime up to 5 gigahertz we use when we experiment in the lab. We have transmitter and receiver antennas, which could be active, which could be passive. When we say it is an active antenna, it requires power. When we say it is passive element, just like your TV antenna earlier, it does not require power, it receives and translates it. Then we have a recorder, which is PC interface, which records the reflected as well as transmitted signal. And we have many types of GPR in the market. We have impulse GPR, which is commonly, if you buy GPR, they will say it is GPR, but they sell impulse GPR, where the source is an impulse, that is nanosecond pulse, and that nanosecond time pulse it is generated. Then we have frequency modulated carrier wave radar, that is, it is using Doppler effect for detection. We have pulse compression radar, where range resolution is improved. We have synthetic aperture radar, which is very good for remote operations. Now we have Chandrayaan being launched. If we want to use GPR on the moon, we have to use this SAR only. We can control from here. It is very good for remote controlling operations and 2D image by beam forming method. Then we have a step frequency radar, which NIRM has got. It is best radar as far as signal processing is concerned. I will explain why. So these are some of the common varieties of radar. Apart from that, people design as and when it is required. Then what is the advantage of step frequency radar? So most of the limitations which we see with conventional GPR is overcome. If we go through the literature, they will say it is the radar of the future. But what we see radar of the future, we acquired in 1995 in NIRM. But its hardware and data interpretation are difficult or a bit complicated. The key to success of step frequency GPR lies in the design of high performance antennas which have ultra wide bandwidth with quick ring down characteristics. These are the design of the antenna, ring down characteristics and ultra wide bandwidth. So if we carry one antenna itself, it will give me a range of 30 Hz to 200 megahertz, which is not possible in impulse radar. That is the beauty with this step frequency radar. And then ring down characteristic is very good. That means it couples with the ground and gives me the signal in all possible cases. Then operating principle, if we see, we have a transmitter antenna, we have a receiver antenna. The transmitter antenna sends the signal into subsurface and reflected signal is picked up by receiver antenna. Multiple reflections are picked up and data is stored in our computer and then it is displayed. So that is what is here. We have coupling loss, direct propagation loss, scattering loss, short circuiting, modulation, many losses are there. So if known effects are muted, that means if we are able to mute the coupling loss, coupling, scattering, propagation, then we can get the target signal enhanced. But in that process, what happens is we are muting 73% of the received signal, only 10 to 15% we are using. So we have a special ways of signal processing in that, and then we get the signal. Then signal is reflected by the target is received by receiver antenna along with all other types of noises. Modulated signal, external source, substrate reflection, kinetic layers, they are affecting the acquired data. So with your expertise or with our expertise, we can segregate the noise and then we can identify the target. So target is not identified by any signature. We can't see anything like if we are able to see a speaker or something buried, we will not see a face like this. It is recognized by the pattern recognition. Some abnormal pattern of signal will come out that we say some target is there. With the assumption that medium response is known, there is ground is uniform and we are getting something abnormal, so something is buried here. That is why use of GPR is not prescribed under conditions where medium response itself is speculative. We do not know whether is some stone is there or some any homogeneity is there, and we want to detect something. We can't say with confirmation that yes, object is there. It could be some hidden inhomogeneity also. So some ideas should be there. Therefore, best suited for defect mapping is just like X-ray scanning, radar is best suited. So if we have constructed some structure and it has damaged, there is no better tool than GPR because we know how this intact will be and we can precisely map the damage. We have used it. I will show you with some case studies. The second problem comes transmitter receiver coupling in GPR. This has varying subsurface condition that leads to the success or failure of GPR. What happens? I have like practical example I will tell you. In this particular case, I have some survey work in this GITAM campus. I have come when we have planned and said if we will come it. When I have come here yesterday, it has rained. Now the GPR which I have planned will not work because ground has become conductive. In this particular case, it will lead to the failure. Now the question is, if I am an expert, I can still bypass that defect part and use that signal and come out with this thing. But if you come with a conventional radar, it will definitely fail because signal will not go up to more than 5 meter depth because 6 hours it has rained. Whole area is drenched. Nothing will go. But the same, if we bring a SFR, we can change our coupling frequency and get the answer. So that is where the TX-RX coupling with a varying surface condition is the key to either success or it may lead to failure, both. So antenna pattern varies with relative permittivity of the medium. So it is expected that electrical properties of the subsurface should not affect the antenna performance. But that is not the case with impulse radar. It affects. And then for effective coupling in the ground, good impedance matching is essential at the antenna and surface interface, which is possible only with step frequency. And this is often ignorantly ignored. Why I am writing ignorantly ignored is, we start using GPR in all conditions and we do not get answer and come back, GPR does not work. Then what happens? What is the transmitter we are talking about? It is a crystal oscillator which generates a pulse of 1 to 50 nanosecond time domain radar. And receiver antenna is a frequency coupler which tunes to the peak power of the transmitter signal. So there is no way we can alter either transmitter or receiver. It has to give the same fixed frequency. So there is no choice, and signal is often missed. So we often end up with recording noise alone and try to build up the target by signal processing, which will all bogus, which gives me all bogus answer. Then when it comes to step frequency radar, frequency, it is a receiver, transmitter as well as receiver signal, both are in frequency domain. So it is a single unit which sends and receives both. There is no coupling error. Antenna is always tuned to the ground. We do not select the frequency as per our antenna. We select the frequency as per ground condition. That is the advantage. We will bring an antenna of 30 megahertz used in this ground. Yesterday it has rained. It will give me a coupling of 200. I will use that antenna for 200 megahertz and get the same answer as it was a dry ground. That is the advantage. So there is no mismatch. But then there is power loss. We add external amplifier to add the power loss. We use long cables to dissipate the noise, and we use time domain transform to get the signal. So there is no error as such. Whatever we see in time domain radar, it doesn't come in frequency domain radar. So what are the traits? What are the features of NIRM GPR is? We were the first institute in India to procure GPR way back in 1995. And practically we have used it in 1996 at Nathpajakri power site. We were the 6th working group in the world to step into the domain of step frequency model of GPR in 1996. Even with limited set of antenna, we have only 4 antennas. NIRM GPR has never failed the expectation. So far we have never gone and come back empty-handed. Always we have come back with result because of inherent hardware superiority. That's why we say it is superior. So what is uniqueness of our GPR is it makes source, it is a coherent source of radio waves, vector network analyzer we are using, and we are using add-on amplifier. We have a very good coupling antenna, and we have open source software which we always modify to get signal processing done. So this is the setup. Technically it is not a radar, it is a lab equipment. We are using network analyzer here at the bottom. This is our transmitter receiver. We add amplifier and we have a PC which records. That's all. So what is being built here is a software which interfaces. So that is the beauty of this GPR. And this is the software which we are using where we can define frequency steps, IF in intermediate frequency, FFT nodes, everything we define, and then we get the signal and invert it and we get the section. This type of signals we get. So because of the tuning capability, I repeat, because of the tuning capability, this radar has never failed. So as explained earlier, ground conditions modify radio signal. GPR antenna tunes for different conditions in different ground conditions. Since source and receiver are independent of antenna in our model, antenna is independent passive element, there is no coupling with the source, there is no hardware on this. So we always change frequency depending on the ground condition. So power can be enhanced externally. So NIRM GPR performs in all conditions. If at all GPR survey is possible, we will come back. If we are not able to do, nobody in the world can do. I can assure that. So how do we do GPR survey? We have biostatic survey where we have transmitter, receiver, antenna as a separate positions, and we keep on moving along a line of survey in the same separation. So this is called profiling from surface with biostatic antenna. Then we can do vertically mapping, that railway pillars we have to do vertically. So we keep transmitter, receiver, antenna getting separate. So it maps vertically down at the center of the antenna. So we can map the defect in the buried pillar. That is called sounding method. Then we can use borehole. From the borehole we can lower the antenna about transmitter, receiver, and we can scan in a direction, which direction crack is there. This is called borehole probing with a guided antenna. We have especially made at NIRM. This is our own innovation. We made with transmitter, receiver, antenna, guided mapping tool. This is what we have made it, guided mapping, where we have given a 30-degree angle only for looking. So if a crack is there, we can see the crack and we can map its profile through the borehole. So from survey types, we can do profiling and sounding from surface. From borehole, we can do profiling and guided probing. And if we use 2 boreholes, we can use cross-hole tomography. We can do non-parallel borehole tomography. We can do 2D survey. We can do 3D survey. All types of survey we are able to do. Coming to tomography, this is another concept brought from medical field in geophysics. So CAT scanning is central axis tomography, which we use for brain scanning. Here tomos means slicing and graphy means imaging. So both we combined, it becomes tomography. And here it is, we can do imaging in time domain or we can do imaging in frequency domain. Both we can do using GPR. And here in NIRM we have developed a tool called monochromatic tomography. We call it frequency domain attenuation tomography, where we use single frequency. And we can enhance the target. The target which was opaque, like we have 7 colors of light, if we use one particular light, it will enhance. So we can use a particular frequency to enhance the target, and we can make it, which was opaque, we can make it bright. So here I am giving one example. We have a target buried. We have 2 boreholes here, one transmitter, one receiver. So one by one, this receiver is moving in one position, then second position, then third position, fourth position. So this transmitter is sending the signal and receiver is receiving it one by one position. Like this, it keeps receiving till it comes to the top. So if you see the target here is traversed by 10 to 12 waves. So next set, we see this position is 12 waves, then second position again 12, third 12, fourth 12, like this we keep on doing. So center position of the borehole is scanned 12 by 12, that is 144 times. This target is illuminated, we think that it is illuminated by 144 waves. So we invert all the 144 transmitted waves together and then we get the picture. And what picture we get will be here. It will be like this. So it is velocity tomogram. We are giving the velocity picture. Same if you give attenuation tomogram, we will get the picture. Picture is blurred depending upon the contrast between the host and the medium. How much it is attenuation contrast, how much is velocity contrast, accordingly it will picture will appear. These are our antennas, step frequency. Now you see it is just fiberglass antenna with the elements here loaded with resistance, and we have a plastic pipe as handle. We connect it to a cable to our transmitter receiver and it becomes, this is hardly, it will be half a kilowatt each. And this is 50 megahertz antenna, supposed to give me 30 meter penetration for 50 megahertz coupling frequency. But I have used this antenna for 200 megahertz as well as 20 megahertz, depending on the ground condition. We can always tune and check and use it. We have different types of antenna. These are shielded antenna, where back scattering is shielded and we can use in covered space like this room, tunnel, everywhere we can use shielded antenna. So as we increase the center frequency of the antenna, the depth of penetration starts decreasing. Then these are borehole antennas, where we can lower the antenna pair in borehole and we can keep changing the frequency by adding extra cable to these antennas. So what are the basic facts? GPR section is a plot of two-way travel time. Signal goes and comes back. We have a record what time signal has gone. We have a record what time signal has come back. So this two-way travel time is recorded. So unlike seismic and electrical method, there is no information about the medium property. We do not know what is the medium. Wave has been sent, wave has come back. So if ground is virgin, we cannot use GPR. It is not good. GPR works only on the strength of the pattern recognition and the time delay. So what is this pattern recognition? Here we say that a specific reflection pattern is formed by sweeping across the target. So as we sweep across the target, as we survey along the line, the reflection pattern will change when we approach the target. Reflection pattern will change when we approach the target. That means if we are hitting a target, maybe we are getting some earlier reflections. So some earlier signal will come. And as we go away from the target, signal will start coming down. So that pattern which is formed, extra pattern by reflection, that gives me the target recognition feature. Then the strength of the magnitude of the signal, that gives me the idea about what type of target it is. So if we do not know the background itself, it will be very difficult to talk about the defect. So interpreting GPR data for virgin area is challenging. So if we know the pattern, how it will look like for a cylindrical pipe, a spherical pipe, we can match, okay, this anomaly is matching with a cylindrical pipe. So object is cylindrical object. This is matching with a spherical pipe. This could be a spherical object. This is a linear object. So if we have, that is called nomogram technique. If we know the specific pattern, we can match it. Otherwise, with our experience, we can say. So it is like an X-ray. where we can distinguish the defect just by knowing how intact it should look like. GPR also will work if we know the intact. If we don't know the intact, interpreting GPR signal will be worse. It needs experience. So where and why to use? GPR is best used for defect mapping. That is mapping known target based on identification of specific geometrical pattern, guided probing which we have developed, and fast data processing makes GPR survey most invaluable tool in troubleshooting applications. It needs proper training for operation and interpretation before use. It is not a plug and play system as yet. So GPR survey may fail if subsurface is totally unknown. If medium is highly conducting, we have constant RF signal in the interference. We have clutter and subsurface reflections dominant. We have presence of multiple echoes in a closed space, and we have range resolution ratio compromised. I will just explain this. That what is range resolution ratio, that I will give little 1 or 2 slides are there. Then we have impulse versus step frequency. Commercial GPR, that is impulse model which we can buy from market. We have hardware fixed on antenna. That is antenna are tuned for a particular frequency. We cannot change it. So for a given ground condition, its performance cannot be ensured. So it may not work in all the conditions. Whenever antennas of the impulse GPR gets tuned to the ground, it will work perfectly like what our works. But if it doesn't get tuned, it fails. Since there is no way to determine that antenna is tuning or impedance is matching, performance guarantee cannot be ensured. So commercial GPR, we call it a flip-flop model, but ours model is always works because we can tune ourselves. Then this is range resolution. How deep to look into? The depth of penetration is governed by the frequency band of operation, what band we are using, dielectric permittivity of the ground, and the conductivity of the medium. There is no thumb rule. It depends on our experience, what frequency we should use and how much depth we should look into. So these are one graph where we have given this range resolution target, and I am not going to explain this further. Here it is written here. Low frequency GPR means 10 megahertz can look target up to 150 meter depth. High frequency above 1500 megahertz can hardly look 1 meter deep. In engineering applications where mostly defect mapping like crack, damage, etc. is there, we use high frequency antenna up to above 500 megahertz. That is widely applicable. Reconnaissance survey, we can use low frequency antennas. So what does it mean? 30 megahertz, 50 megahertz is used for reconnaissance survey. Engineering defect in construction, we can use 250 to 500 megahertz, which will go to 5 to 10 meter. And crack or fracture or tomography, we have 1500 megahertz, which is within 1 meter depth. Then resolution is the ability to distinguish target at various depths. Many times I have come across cases where we will see that in urban area we have to map utilities. That means some cable pipe is buried, we have to map a GPR. Okay, it is very good. Then we say one pipe above another is buried. One pipe is at the top, another pipe half a meter down, then 2 meter down. How many you can detect? That becomes resolution here. The resolution is the capability of GPR to distinguish two closest event from two event, which is closely spaced to each other. So GPR and resolution is that is frequency divided by twice of bandwidth. So if we increase the bandwidth, we can increase the resolution. That is the advantage with our GPR. We have ultra wide bandwidth. So our resolution is the maximum. I will just give this example here. In impulse GPR, it is trade-off is 1 by 10. That is, if we are mapping 1 meter depth, our resolution will be 10 centimeter. If we are mapping 1 kilometer, it will be 100 meter. But in step frequency, we can give you 1 by 100, 1 by 15. That is the advantage. 1 by 15 resolution we can give it. So these are the target size and different frequency. So 1 meter we can give 0.1 meter, 2 meter, 0.2 meter, 5 meter, 0.3 meter, 10 meter. This range I have given, and what is the target size we can give. That means from this table, there is an inverse relationship between probing range and target resolution. So it has a direct bearing on the depth of investigation. So technically what we say in layman terms, we should not look for a cricket ball at 1 meter depth, because at 1 meter depth we should look for a target of 10 centimeter at least. So if somebody is saying my cricket ball is lost at 1 meter, if you use GPR and say it is detected, that person is cheating. Theory doesn't support. So we should experiment only when our theory supports. Perhaps this is ignored by most of the end users and they come back with some image and say it has worked, but it is not this correct signal. So in majority of the cases, it has been subjected to compromise with the resolution users and then it has failed. Almost all R&D institutions in India has a GPR today. But success is not so much. So it is very important to know not the capabilities but limitations of the GPR before buying a GPR. Everybody knows the capability. What the limitations are not known. If we know the limitation, we can use is the best. With this backdrop, I will come across some case studies which will be of interest to you how it has worked. First case study I have brought is from oil pipeline from Asansol near Calcutta. The case here is, I can explain with a picture. There is an oil pit burning here and just 5 meters away from this pit a pipeline was going. Oil pipeline, Haldia Ranigram Baroni pipeline. Haldia Baroni pipeline is going. The IOCL was worried that if pipeline is under the influence of this fire, it will be non-controllable. So they gave contract to ISRO. ISRO measured from the satellite and say pipe is under fire. They see from satellite, they don't see on the ground. Immediately the refinery was stopped and they were searching who will look into the firework. No institution works for the mine fire. So many cases are there, I think. He was explaining the fire cases. If the moment they hear mine is under fire, no, we do not go. Without bothering that what it is. They came to NIRM. I said, let me see what it is. When I saw this was a pit fire, somebody was doing brick clean and this caught as fire. We will investigate. We investigated using, this is the crack appearing on the surface after 4 days. And exactly on this line, this pipeline, this pipeline was going. And we did this survey. You see, same antenna we are using. We did this survey along the entire pipeline. And what we got is from the surface, we are getting the cavity pockets which is reaching as shallow as 2 meter depth it is reaching. So I said that ground is caving in and the effect has come up to 2 meter and pipe is at 1.5 meter depth. Anytime it can come. So we have to isolate that zone so that it does not come. Fire cannot catch in soil or sand. It is only in coal it can catch. So what we said is we have to make a deep cut and fill it with sand and we will isolate that fire. With so many surveys, all the cracks we are seeing appearing, we got it packed at 4 places and till today it is operating, there is no problem. So the answer is we cannot run away from the problem, we have to give the solution. Fire will be there, pipeline is still there. They were measuring temperature of 78 degree. When we went to the ground, it was not even 20 degree because it was from satellite they have given the picture, not from the ground. So the question is, we have to go to the ground and see what is the condition and we cannot run away as a scientist, we have to give the answer to the industry. They were losing 1 crore per day by shutting down the refinery, just for the fear that my pipeline will burst. So what we found from the GPR survey is, there is no threat to the stability of pipeline. 2 gravity pockets formed and other suspected anomalies were recommended for immediate packing. Further investigation recommended, I said that entire 42 kilometer route of pipeline passing through Raniganj coalfield should be investigated for such type of coal fire issues and periodic monitoring should be continued in vulnerable zones. Second survey I brought is for landmine detection at Chhattisgarh. This is very interesting story. We got a phone call from Governor of Chhattisgarh that NRM is the capability and we have Dantewada repeated problem of landmine blast is there. Can we do this? First we said we do not do because the letter has come, you have to do this, we do not pay for anything. I said we are not working under them, we will not work. We will not do. One fine day call came, he says, I am Governor of Chhattisgarh speaking, I want this. We cannot say no. All the way we went there, they have showed me these are the landmine blast here. And what he said, Governor, is, he was an ex-IPS officer, the person I am talking about. and he said that I have buried some live landmine for you. You have to do the survey, flag it, and my bomb disposal squad will be there with you. He will defuse the bomb. The person who has laid the landmine will not be there to help you. Okay, we have to do the survey. What to do? Then we started doing the survey. So digging was done at several locations so that we cannot say here is a landmine. Everywhere they have dug and left it. Confused me. Then we have done the survey in a grid manner like this, all the ground. And all along this line we did the survey. We could clearly identify the sweep zone and this target. So when it was dug out, this is a plastic mine. They have buried the mine with a tiffin box, some plastic bag, so that it is not detected by their metal detector. They wanted to know GPR can detect or not. All the 6 mines we have detected, it was diffused by BDS in our presence. They recorded the video, gave me some trophy and certificate, and we came back. That's all. Now they are procuring drone-based GPR for landmine detection, but problem is still not solved. Because problem is still there. We want automated system. We can do it with the setup developer. The third is archaeological remains. This is in Bangalore Metro, where if you have heard about the Bangalore Metro, it is crossing between two iconic area, that is Tipu Palace and Tipu Palace and Tipu, what is that? Two places it is going. It is between Vanivilas, lying between historical archaeological Tipu Summer Palace and Tipu Fort. In between two, this tunnel was going. Our ASI said we will not allow tunnel. Why? This area, all my weapons are buried. Who buried Tipu Sultan? He died long back. But they say it is buried, we will not allow. Then tunnel has to go, alignment cannot shift, metro has to go. They requested NIRM, we went there and surveyed. We identified 2 locations where there are suspected target, and we said it should be allowed. For that we have to go to Delhi, present the report to ASI and get the clearance for VMRCL from ASI. They cleared it, and the places where we have marked, this is the Tipu Fort and Tipu Palace. This is one is fort and one is palace. This is palace, this is fort. Wherever there was space, we use the same antenna what we are seeing, fiberglass antenna. And we mapped clearly the pattern recognition, 2-3 places we are getting the pattern suspected. If you see the newspaper, in this location they got Tipu era cannons. 2 cannons were detected. They kept it in a museum. That was the agreement, that if we get anything, it will be kept by BMRCL in a museum. They will not destroy it. That's all was there. For that they were not allowing the tunnel. So GPR survey has helped. Next case is from Mumbai Metro we are getting here. Here in Mumbai we have lot of water problem. But in Marol area, whenever they constructed a tunnel, when they were constructing a tunnel, continuous water seepage was coming. They do not know where from so much water is there, because all areas water scarcity. And on the top, metro is already running, bottom second line is going. They had the idea that if little bit ground shakes, everything will go. So all the pillars were getting monitored, and they asked us to do survey. I said IIT Mumbai is nearby. Why we should go all the way from here to Bombay? You can get it done. We have a geophysics department. No. NIRM should come. We went there and did some cross-hole survey, because in Mumbai there is no place to do the survey. Whole night traffic is there. We did some borehole in the ground, and night time we have done from 1 o'clock to 4 o'clock. 3 hours only we got the slot. Night. We did the survey, and we could map the damage, this water infused zone. And if you see the 3D picture, it is clearly showing that this is the point of leak, and here is the water cluster, and from here it is coming down. So what we could suggest them, that we have to put a blockade here in this particular, we provided a hole where they have to block it, and they blocked it, water seepage stopped. And today this area is through, they have gone ahead. L&T was doing, but the problem comes, they want solution immediately, because it's a construction related problem, and no other method will work, because if we do seismic, it will damage further, because there is a tunnel, there is a metro system going on the top. If we do other methods also, it will interfere. Electrical, it will interfere. So GPR is the best option. We got it done. Next case is in Bangalore. We are using a Tata Promote Society. This is a very, very costly luxury apartment society. Each apartment costs 3.5 crore to 5 crore. That is the minimum cost of the apartment. And what happened when they construct the apartment, the approach road is cracking. Every rainy season it will crack. Everything will be washed away. They do not know what is the problem. So finally the apartments were not getting sold, many apartments, because there was no approach road. Then they asked us, can you help us? We went there to do survey. What we could find them, that entire area has been developed by cutting a hill and they have blocked the water flow path. As simple as that. We did the survey and found that 3-4 pockets in GPR survey we could find that water flow path is getting blocked. In seismic survey, resistivity survey, everywhere we got the same thing. And we said that you put slotted pipe and allow the water to flow. 3 places we have given location, they have allowed 24/7 water is flowing like a fountain, and last 3 years there is no damage. As simple. But ignorantly they have made, and every year it is losing. Because of that, nobody was going to buy those flights. And big people have already purchased before construction. But post that, we cannot go. 3 months we have to stay in the house. Road is washed away. That was the issue. So these are the cases where we have applied GPR. Then next comes here. Vardhaman in Gujarat, where we had done GPR tomography. This is from Prime Minister's constituency. He is from Vardhaman. That Narendra Modi is from this particular village. His house is there. Whenever we went, the people showed me his house. There is a board. It is earlier house of Narendra Modi, like that. He belongs to that village. The problem here is it is a Buddhist monastery. When they dug out, a lot of Buddhist monastery site appeared. And in the scriptures of Wensang, when it came to India, he has mentioned that all around the area there were Buddhists living there. So the Prime Minister wants to make a Buddhist circuitry. Japanese government is ready to invest. And they started digging out. Most of the places it failed because nothing was appearing. Then they approached us. We can locate some areas by GPR survey where we can do digging and find out. Okay, we will do. The work was given to IIT, then it came to NIRM from there. We started doing the survey, and we have done borehole survey, we have done the surface survey, everything. You see, surface survey, we have gotten the clusters of damage. When we generate 3D image from borehole survey, we can see clearly some collapsed structure below, some pillar has collapsed. We have marked those areas that there is some structure collapse. They have dug out, and everywhere they have found a structure. It is coming up at a museum. This has been documented in Discovery Channel. They have taken 2-3 minutes bites from me also. That is coming in 16 language, this video. And now the Ministry of Culture has put NIRM in their committee for future excavations. We should help them by GPR survey. So this is very simple work. But because of ignorance, people are not able to do. And here we have shown that with simple survey, we can plan instead of digging everywhere. We have to dig where it exists, so that success rate is 90% from what is getting 20% today. Then here it is a mining area. We have done GPR survey for finding out the old workings from Rajpura Dariba mines. Here they wanted to locate the old working from the mines and some water pockets, zones where inrush of water was there and it was plugged. Now they want to know up to what extent the old working is there and how we can mine that. So what we have to do is we have to go down and drill boreholes everywhere, and through boreholes we have done the survey. Between 2 boreholes we have done the survey. And we generated this GPR picture, and finally by generating all the pictures, we came down to this final picture where we can see this attenuation zone and ores area. So what we have shown is in this area water lock is there, and otherwise it is all remains where we can mine out. So they have sealed up that water content area, and remaining area they are able to mine. So whatever mine ore was locked, they are able to mine out with this survey. This is in Koldam Hydel project in Himachal Pradesh. This is in Koldam Hydel project in Himachal Pradesh, where it comes under NHPC. When it was constructed, it was looking like this. But today, the entire thing is washed away. This area, this spillway. Also, if you see everywhere, crack is appearing, it is collapsing, joints are opening. And they have put crack monitor, how it is moving, and today we are getting the information that cracks are as wide as 30 centimeter to 90 centimeter. I don't know, 90 centimeter is a crack or opening, I don't know. So this is the situation, and they wanted us to do GPR survey because all other survey will damage it further. Now this is a RCC platform. Iron is there, we cannot work. So all other companies have come and gone. We started working on that and we give them the picture. This is the area we have worked in this RCC platform, and we got all the damage zones wherever it was there. Weak zones, damage zone, crack zone, everywhere we have shown. And we have marked all those in our section, and finally we have shown the trend where it is going. So 9 cluster of anomalous zones were mapped, and it is in the continuing up to lower level, 20 meter, 30 meter level. So what we have written is that damage zone is not from surface, it is going further deep and it is allowing water to flow. Today we have come to know that water is flowing from the bottom. That time we were advised to do seismic survey and get it sealed. They ignored, but today they are facing the consequences and they have to do some extra measures to protect it. This is from Tala hydroelectric project in Bhutan, where we have done GPR tomography in the crown area. Normally we do in the subsurface, but here we have done that crown of a tunnel, where we have used 2 boreholes to do mapping in the crown to find out the effect of a crack which was appearing in the crown and how deep it is and what is the effect of it on the stability of the tunnel. So when we generate the picture, we could see that picture. This whole area is damaged and it is a plastic zone and fractured zone, and this crack is water is appearing to flow in this direction. So what we suggested is this entire roof of the crown has become a weak zone. We have to stabilize it. So finally they have stabilized and gone ahead with construction. Otherwise this whole area was failing. This is in your Andhra Pradesh, where we have done the Sri Salam Dam study. You see this Sri Salam Dam, this is the apron of the dam which was at this alignment. Due to wrong design, whatever we say wrong design or continuous use of water discharge, this whole area water was discharging and it has eaten away this apron. They tried to protect the front. If you go there, there's iron cylinders are protecting the front face. But after 2 years, the bottom of the dam is washed away, and underwater videography has shown that it is eaten 400 meter into the dam axis. So they have asked us to map the cavity zone so that they can take up the repairing work. No problem. So we have done this GPR survey on this. This whole area was waterlogged. We have put a bamboo ladder. On that we have done the survey. We have confirmed a seismic survey. We mapped all the wide zones. And finally we have given them the cavity, that is 4,250 cubic meter of cavity. When they packed it, the total consumption was 4,500 cubic meters. So it has mapped. Today, after 15 years, again it has gone down. So they are again asking us to do the survey. There is no other agency which can do the survey. This is from Bangalore refinery, where we are mapping GPR survey on an iron tank pad. This is totally impossible. Nobody can map on a 16 mm iron plate. We have done the GPR survey, and here what we have mapped is this cavity pockets in below the tank pad, which is allowing the tank, which is making the tank to collapse repeatedly due to loading condition. And when we mapped this cavity, it was grouted by IIT Mumbai. After grouting, they again asked us to find out grout is proper or not, because civil engineering we can only grout. We cannot say grout is proper or not. After that, we again checked it, grout is proper or not, and what we could find is, these are the cavity blue dots where it has not yet reached the grout. So we have said that grout is not proper. These are the locations where we have to grout it again. So with all this grouting done, till today tank is intact for last 7 years. So after repeated failure, GPR result has proved them that it can be used. So like this, we have many more case studies. I will end up here with our presentation. Thank you.
Thank you so much, sir, for enlightening our students and the participants from outside with the concepts and applications of GPR. Now I request Professor T. Madhavi, convener of this workshop, to present the memento to Dr. Jha. PC Jha. And I request Dr. C.H. Akhilesh to join them. We have a lunch break now for 1 to 2. After the lunch break, we have 2 more sessions along with valedictory and high tea. I request the student volunteers of GITAM, Mr. Pranav, Abhishek, Manikanta from boys, and from girls, Shrujana and Satvika, to guide the outside participants to the GITAM Cafe for lunch. The lunch has been arranged for outside participants at GITAM Cafe. I request the student volunteers of GITAM to kindly guide them to GITAM Cafe. The faculty from OU and Malla Reddy, please join for lunch with GITAM faculty. Outside participants, please be seated over here so that our student volunteers will guide you to GITAM Cafe. I request outside participants to be here so that our students will guide you to GITAM Cafe. I request all the participants to reassemble in this hall by 1:50 p.m. for the next 2 sessions. I request all the participants to reassemble in this hall by 1:50 p.m. for the next 2 sessions. Thank you.
Good afternoon, one and all. I deem it my privilege to introduce our esteemed guest, Dr. Ajay Kumar Naitani. Dr. Ajay Kumar Naitani did MSc in Geology and PhD in Engineering Geology from H&B Garhwal Central University. Presently, he is working as a scientist and head of the Engineering Geology Department at NIRM Bangalore. He has been actively involved in the field of engineering geology and landslide hazard assessment for more than 30 years. As a PI and co-PI, he has successfully completed 5 R&D projects sponsored by Department of Science and Technology and Council of Science and Industrial Research. He has made important contributions for the development activities in 21 watershed projects of Uttarakhand, Himalaya. As a project leader and coordinator, he was associated with some of the important hydroelectric projects, India's first type underground crude oil storage rock cavern projects, atomic power projects, lift irrigation schemes, roads and railways tunnel projects during DPR or construction stage investigations. Dr. Naitani has more than 113 scientific papers and 24 popular articles to his credit, which are published in national, international journals and proceedings. He was conferred with the Young Scientist Fellowship and Senior Research Fellowship by Government of India. He is the recipient of the prestigious Young Scientist Award from Government of Uttarakhand for the year of 2007 for his distinguished contributions in the field of geology, GSI Sesquicentennial Commemorative Award from Geological Society of India for the year 2009 for his distinguished contribution in the field of engineering geology, Indian Science Congress Association Best Paper Award for the year 2015 to 16 in the section of Engineering Sciences and Indian Society of Rock Mechanics and Tunneling Technology, Best Paper Award for the year 2019 under the category of Case History of Tunneling and Foundations on Rock. He is Associated Editor for the Journal of Geological Society of India. Presently, he is a member of Bureau of Indian Standards and Technical Evaluation Committee of National Disaster Management Authority, Government of India. I kindly welcome, I kindly request Dr. Ajay Kumar Naitani to deliver the lecture on engineering rock mass classification for underground structures and foundation. Yes, sir. Kindly please.
Respected sitting in the front row and faculty member of the university, my dear friends, all the students sitting here and they joining online also. So after good food, it is very difficult to sit and listen, and I will try to make this presentation comfortable for you. And this subject is we have selected for you people because in your course, in your syllabus, you people are reading regarding the rock mass classification, different type of the rock mass classification. And from this lecture, what the management and you people can think that suppose it is not in the syllabus, that it has to be included in the syllabus. So whatever I am going to give a brief about the rock mass classification, these classifications are being used worldwide, and we in India also in ourselves in NRM also, we are using this classification since the beginning of the setup of our organization. So this I have selected the underground and the foundation only. The another aspect which is very important is the slope. But because of the time constraint, that slope I am not going to cover, and I will cover only the underground structure and the foundation. How it will change up and down. So you see, in general, if you see, these two words are very commonly being used. And sometime I've seen that people are not using the properly. The terminology should be very proper. Then one is the classification and another is the characterization. So both the meaning have a different this thing, that the classification, and what I am going to give a presentation that is on the classification only. And what is the meaning of the characterization? The characterization, my previous speaker, Dr. Jha, told you about something about the one tool of the investigation in the geophysics, whatever we are using. So many tools are there which are being used for the investigation of Mother Earth. So the classification, what should be the definition of the classification? Whatever the parameter are being used, we are collecting real data. We are collecting from the site that are being used to classify a rock mass. Now the question is why this classification is required. If you see, I am an engineering geologist, but in my front, maybe the online, so many engineering geologists will be there, but in my front, the civil engineers are there, the minings are there, and the mechanical engineers are there. Whether they have a very limited idea about the rock mass classification when we are using the particular term. So what should be a terminology actually when we are using, this is a purely the applied field only. So when we are using this classification at the site, what should be the terminology, common terminology we should use? And at the project site, if you remember, the project site, my crew, sometime illiterate. They are not having a well education, well background from the engineering. So this, what should be the nomenclature for the rock? That is called is the classification. The classification means good. Everybody knows what is good, what is bad, what is extremely poor, what is poor. So this type of, again, that was refined. And the project site, what the terminology we are using? We are using class 1, class 2, class 3. And if you Google what is the class 1, you will not get a definition. What is the meaning of the class 1? The definition is not there. But every project site, you will see that the rock will be characterized and classified that what is the rock class, that would be class 1, class 2, class 3 and class 4. Now the characterization at the site, whether we are collecting all the data, the engineering geologist is collecting all the data. No, we are not collecting all the data. We are collecting the data that is pertaining to the mother. That is they are the discontinuities, the nature of the discontinuities. If you see the rock stresses, the different setup of this thing is there, from where we'll come to know that which type of the stress condition, which type of the pressure will be there to concern to the excavation. Whenever we are talking about the undergrounds means mainly either it will be the tunnel or it will be the caverns. The caverns means the morning speaker, Professor Sastry, my honorable director, told you regarding this cavern. So cavern means a big size cavity. And the big size cavity, the most important parameter is the stress parameter. That should be known to you. And the stress, that is why it is important, if you remember the word used by my honorable director, the orientation of the longest axis of the cavity will be decided by the in situ stresses in collaboration with the joint orientation or the discontinuous orientation. We come to know about that one using the stereographic projection. That is a very important exercise. All the civil engineer, engineering geologist and the mining engineer, they are using that type of the tool. And then the permeability, the second parameter, if you see, the two words are being used, the total stresses and the effective stresses. You know the difference, particularly the civil engineers, because the same terminology in the civil generally, we are very well in the soil mechanics. In the rock mechanics, the difficulties is this, that soil mechanics, the material is the homogeneous. But the rock material will not be the homogeneous. There is a certain condition when the rock can be homogeneous, and that condition will not get at the site. Where we are going to execute my project, where we are going to make my tunnel, we will not get that. So that these discontinuities will play the very important role regarding the permeability. And when we talk about the effective stresses are the total stresses plus my pore water pressure. That should be known to you. And the third parameter is the seismic velocities, means my mother characteristic with regarding to the velocities of the waves. The waves velocity from where we'll get from the geophysical tool. And the most important part, then the sample, the rock sample, that is the rock also known as the rock material, that has to be tested at this laboratory. And then the rock material, means the in situ rock, that has to be converted into the rock mass. So when we are incorporating all the data, that is the characterization of the rock mass. So this is way of the difference between the classification and the characterization. Now this Now the question is, what is in the morning also somebody was telling that the rock looks very good. But the scientists and the professionals, they are telling that rock mass is not good. Then what is the difference between the rock and the rock mass? And how this rock mass system actually, this rock mass system is developed over the years. And then what are the applications of the rock mass system and what are the limitations of the rock mass system? So this I am going to cover in this lecture. The rock mass is simply, that is again a very famous word, the scale effect. If you remember this scale effect, when the scale is increasing, suppose we are taking, suppose that we are making a borehole. In generally, again, for you, the student should know that always we have to follow some standards. Research is the another part, but when we are going to execute and making a project, we have to follow some standards. The some standards means, suppose we are going for the drilling, then what should be the dia of that drill borehole? So this should be as per we have the BIS, Bureau of Indian Standard. Again, we have the ISRM standard. In International Society of Rock Mechanics and Rock Engineering, we have to follow some standards. That size is, you see, when we are making a borehole, that is the dia which is referred in the ISRM also, ASTM also, and BIS also. The rock has to be tested using the NX only. When I am using the word NX, means that the size is fixed. It is a 54 dia only. The size of the dia cannot be less and size of the dia cannot be more. So you see, it is a very small. But suppose somebody is telling, we are making a borehole, but what we are going to make? My aim is either to make a tunnel, either to make some foundation, say nuclear foundation or any sort of the foundation. It will be a big size. My borehole is very small. See, when the size is big, and the concern, borehole, right now the concern is borehole. That is a very small. So when we are looking after this very small, it is not having all the characteristics of the discontinuities. So this is an intact rock when it is not having any sort of the discontinuities. Discontinuities means joint, you can take it as joint, you can take it as a fracture, except the fault, like in the geology, we call it the fault or the shear zone. The shear zone and the fault is having the different meaning than the discontinuities or the joint. Any sort of the fracture which is not having any sort of the displacement, we call it a joint. When it is not having any joint, and again you people have to remember that all the rock sample, whatever we are collecting from the site for the testing, they are having the microfracture. And as per the international standard and the Indian standard, we are not considering the microfracture into the consideration. That is why it is the intact rock. But when we are having the bigger size picture, you see the big size picture, the same rock type must be same. Say in the Telangana, the maximum portion of the Telangana is covered by the granites. Granites means, if you see, the strength of the granite is more than 200 MPa. But when we'll go for the making some structure, underground excavation, whenever we'll do, and whenever we'll make the foundation also, we'll have so many problem in the foundation or the underground excavation. Because the same granite, which is very competent, the rock is very competent, but when we are making a structure in the bigger size scale effect is being used, that is converted into the rock mass. So the difference is very simple. When the rock is having the different set of the joint, and when it is not having any set of the joint, we call it as the in situ rock. And when it is having the discontinuities or the joint, we call it as the rock mass. Now the important part, whether the importance has to be given to the intact rock and whether the importance has to be given to the discontinuity. That is again the important. Now this thing, if you see, for the design, if you go, any sort of the rock mass classification is being used. For what is being used? Actually, this parameter will be used for the classification. Whatever the data will get, the designer will use for the design of the tunnel or the cavern or the treatment of the foundation. In the foundation, the design will be for the treatment. And whenever we'll talk about this thing, underground excavation, we talk about the design of this thing, that how to protect the crown and how to protect the walls. That the walls and the crown will be the different sort of the things. And this intact rock as well as the discontinuity. You see the intact rock properties, so many properties are there. The civil engineers are sitting here. Suppose I will say that what are the important, all knows that one, that UCS is the very important property. What other property, the intact property, means which should be known from the laboratory. That is the modulus of the deformation or the modulus of the elasticity. In general, if you see, we'll get a modulus of the elasticity, and there is a difference. If people know, there is a difference between the modulus of the elasticity and modulus of the deformation. And the difference is this, that when we talk about the modulus of the elasticity, means we are taking into the consideration only the elastic values of the deformation. When elastic and plastic, both the type of the deformation are taken into the consideration, that goes to the modulus of the deformation. So this parameter you will get from the intact rock. But the discontinuity, whenever we'll talk about the discontinuities, they are the shear parameter. Means the strength, which the parameter, which factor is going to control your stability in case of the underground excavation as well as for the slope stability point of the view. So the shear strength parameter is going to control your the stability. The shear, when we talk about the shear strength parameter, only two parameters, C and phi. So C and phi parameters are very important, which should be known for each joint set. And through your experience only, you will come to know, suppose we are having the 2 set, 3 set, 4 set or 5 set of the joints, which set is going to create a problem during the excavation and during the construction of your underground excavation. Now you see the how many parameter there's this thing pattern and the relationship you can see. So there are the different thing that how we can go for the collection of the data for the rock mass, the characterization or the rock mass classification. So each suppose I am having the length of the tunnel of the 10 kilometer. So how you will characterize the 10 kilometer tunnel? First you have to define, you have to divide this 10 kilometer into the different sector, different domain based on the similar type of the geological characteristics of the mother. So after this thing, for each domain, you have to collect the data. Now, this thing is the thing is what is the difference between the rock, the mechanics and the rock engineering. So I will not go in very detail because time is very constant. So you see this is divided. The 16 blocks are given here, and out of the 16 blocks, you see the first 9 blocks belongs to the rock engineering, and rest of the blocks are related to the rock engineering. So the rock mechanics and the rock engineering is totally different. They are interrelated to each other, but both this thing are not same, and that is the only reason. If you remember, earlier this ISRM is known as the International Society of the Rock Mechanics only. Now it is a International Society of Rock Mechanics and the Rock Engineering. So this is what I told you in this thing that the beginning of my talk, that what is the scale effect. If you see on the top, you see the size of the in case of the underground, or on your left, the tunnel excavation, we have to make a tunnel. On the right, this is a slope stabilization. So if you concentrate on the left, we are concentrating in a very small area. Suppose in the top, intact rock, it is written. So intact rock means no, it is not having any set of the discontinuity. When the size is increasing, we are increasing the size, the number of the discontinuities are increasing. That is why this rock mass, where we are going to make our structure, tunnel or the cavern, that structure is having the multiple set of the discontinuities, and that is known as the rock mass. So being a rock mechanics engineer, being the civil engineer, mining engineer or engineering geologist, we should never talk about the rock. The very strong rock may be a weak class. It may be a very weak rock mass, but the weak rock mass doesn't mean that it is the weak rock. So the difference should be known to this thing. Again, this is the example. Suppose at the surface we are making some sort of the excavation. So which type of the changes it should be in your mind? When at the surface the size of the cavity, the excavation is increasing, which type of the problem you are going to face? If you see on the left, as the excavation dimension is increasing and the discontinuous spacing is decreasing, the stability, the point of the view, it is the more dangerous. But when you go deep on your right, what it has shown that on the surface, which type of the failure you can expect. And when you go deep and deep and deep, the stresses problem will be there. So at the surface, the problem will be different. And when you go deep and deep, the problem will be different. The problem is related to what? The problem is when the problems are different, their supporting system will also be different. The same system cannot be applied for the different type of the conditions. Now you see, yeah, suppose at the surface, at the low stress level, suppose we are making a structure, and at the high stress level we are making the structure. So on your left, at the 3 column, it is written massive rock, jointed rock, and the heavily jointed rock. So in the low stress condition, what I am telling, 2 words are written, that is the low stress and the high stress. The most suitable condition is the medium stress. That is the only region. So lot of the investigations are required. Our target will be to put my structure where we want to make our structure. It should be, we try to fit that structure in the medium stress condition. So suppose the condition is medium stress, the excavation is the medium stress. During the excavation, you are going to face a less problem, and your support will also be less. When you either it will be in the low stress or in the high stress, in both the cases you are going to face a major problem, and your support system will also be the more. So that is this thing, that why the investigations are required, the detailed investigation are required, and the characterizations is required. This is again, a flow chart is shown here, that is the how to characterize the rocks, as already spoken to you regarding that, which type of the factor we have to take into the consideration when we are talking about the characterization of the rock mass. Again, when we talk about the characterization for the slope, it is totally different when we talk about the foundation and the underground excavation tunnel or the cavern. Now this is the parameter, the most important parameter, what are being collected worldwide for the classification of the rock mass. Any type of the classification you will use, we have to know the strength of the intact rock. Now the many things should be very clear. Whenever we talk about the strength, it is the strength of the intact rock. We are not talking about the strength of the rock mass. Only the intact rock, whatever we can determine at our laboratory, that is the strength. Now spacing is very important parameter, and the condition of the discontinuity, little bit I will elaborate on that one. And the orientation is very important with respect to the tunneling as well as for the slope. And the groundwater condition, again it is a very important parameter, as I told you, how it is affecting the stability, how my effective stresses are changing with the change of the groundwater condition. Now these are some eminent people. The Tarjagi is the father of the soil mechanics, and the Benowski, the RMR, I think that will be in your syllabus. The Benowski has developed this RMR and this RQD, very well known terminology, rock quality designation by the Dr. Deary, and the Q tunnel quality index by the Barton team, Dr. Nick Barton team. And that is the JSI and the who people are involving in the rock mechanics field. The Hook and Brown failure criteria is very famous, and I am not going to touch that one. Only one parameter, that is the GSI, I am going to cover in this thing, and that is by the Abbott Hook and patches, that is the NATM. If you see across the Himalaya, in Telangana, whether you are Devadula lift irrigation or the Kaleshwaram lift irrigation or the any other lift irrigation in Telangana, whatever we are using, we are using the either the tunnel quality index or the RMR. We are using that one. This NATM we are not using here. So NATM is proposed by the Patcher, and the Professor Patcher, later on it was modified. Across the Himalaya, if you see in the Himalayan terrain, the people are using the NATM classification. So these are some of the classification. Even today, this 1946 Tarjagi rock load classification, even we are using today in the certain with a certain not everywhere. And a lot of this classification, the only few classification I have mentioned here, which are being used worldwide, and the most important is the Q, the classification by the Barton et al. And some modifications are done with respect to the different purpose. The different purpose, suppose if you see this is Q classification, this is originally made for the underground excavation, tunnel and the caverns. Now it is modified with respect to the excavation also. Which type of the tool can be used for the excavation point of the view, that also was done by the Christian. Now this is the RMR. If you see the coal mining in India, the two modification with respect to our coal mining in the RMR, it was done. and that is by the Ghosh and Raju, and another is by the our former director Venkat Shorlu. So these two modification, but in the civil project, whatever the original proposed means last modification, this Banowski has done the last modification in 1989 for the rock mass rating classification. Now this is the Tarchagi rock load classification. Only you should know that what is the meaning of this thing, that he has characterized the rock mass into the different categories, but these categories are not applicable right now. What is being used? What is being used? This is being used, that how much load actually, where we are using this thing, where one should use this thing. Suppose we are making a tunnel and your tunnel is open to sky. Whenever your tunnel is intersecting by the some shear zone and you are unable to project that one and unable to protect in time, because the ground, this mother is having a certain time it will withstand during the excavation. That is known as the stand of time. After suppose up to that time the tunnel is not supported, that definitely it has to collapse. So how much pressure it is going to come, you that this classification can be used for that point of the view only. Rest of the things we are it is not being used across the world. Now this is a the limitation, as I told you, the limitation of this thing, that when it was proposed, when there was no concept of the shotcrete and rock bolt, means only one concept of the underground support was there regarding the ribs in form of the iron support only. So that time it was used. Later on then, when the concept of the support was changed, this classification is not being used anywhere. Now this in the Loeffler classification, the importance is this this name should be remembered for this thing only, that the stand of time was first time given by this thing, and later on actually this modern NATM foundation is on the Loeffler classification only. And this is the limitation of this thing, that how much the support has to be given for the particular rock mass classification. It is not defined and given in this classification. Now this is the NATM. Now this is the important, because worldwide it is this classification by RQD. This is itself is a classification, but this formula is given here. Everywhere you will get it, this one across the world this is being used. And there are two type of the method to get a RQD, rock quality designation, either from the borehole, and this empirical relation is also given. So from the surface, if you have the volumetric joint count, if you have the JV is nothing, but in this diagram, in this cube, it is shown that how you count the number of the joint set. If you count the number of the joint set in a one cube, that is joint JV, volumetric joint count, then this is the formula given, that RQD is equal to 115 minus 3.3 into JV. So worldwide it is being given. People are doing the research, but for the practitioner or the practical point of the view, this empirical correlation is being used. And this some sort of the first time for the with respect to the RQD, some support system was given, but it is again not a fulfilled classification. And the limitation is the one-dimensional parameter only. That one parameter cannot be used for the classification point of the view. And ultimately, we are thinking for the characterization of the rock mass. If you are thinking for the characterization of the rock mass, one parameter. But this parameter is a very important parameter for the other classification. Now this is again the RSR classification, that is the rock structure rating. Again this classification is not being used. Why I have mentioned here that the first time the word shotcrete was introduced in this classification, that this shotcrete, how much load shotcrete is going to take. So the importance of this thing is given, and based on the three parameter, means the geology, geometry and the groundwater condition, the rock mass was classified by the Wickham et al. Now these are the three parameter, and if you add all these three parameter, you will get the RRS. Now, now this is the most important parameter. In this parameter, this is the RMR. I think it must be in your syllabus. The 5 parameter plus 6 parameter is the orientation of the discontinuities. That is the adjustment factor actually. And these are the parameter, and these ratings are given actually. These all are the empirical the relationship, empirical formulas are being used to characterize the rock mass into the different classes. And if you see the intact rock, the values are varying from the 0 to 15. And for the RQD, this is the same RQD as proposed by the DD. The same thing, the values are given from the very poor means it will be 3, and maximum the 20 are given. For the spacing of the discontinuity, again the minimum value 5 and maximum 20. And the groundwater, this is the 0 to 15. So means if you add all this thing, and finally this is the condition of the discontinuity. Originally this classification was proposed with the normal condition of the discontinuity, but again this one you can characterize based on these parameter. The first parameter is the persistence. What will be the persistence of the length? Persistence means the length of the discontinuity. What will be the separation between the two discontinuity? What is the roughness of the joint surface? What is the filling in between the joint? And what is the weathering? So these are the parameter. The lot of time is required at the site, project site, for the collection of this thing. And as I told you, for the open this thing, we have to divide into the different domain, similar type of, which should have a similar type of the geological characteristics. But for the underground excavation, it cannot be more than 5 meter. In case of the foundation, it cannot be more than the 2 meter. In case of the nuclear power plants, it cannot be more than 60 centimeter. So you see, this is a scale sort of the effect. For foundation means every 60 meter, you have to collect all these data. In case of the tunnel, every 5 meters. So we have a tunnel, means suppose we have a tunnel. So when you are making the excavation in the morning, first lecture by our honorable director with the blasting. So what is my sequence? My sequence is, we'll make a borehole, a drill hole, then we'll make a blast, then the diffuming will be done, means this gas, it should come out, and then the next will be the scaling. Scaling means some loose portion, particle will be there. That loose particle has to be removed from that excavated area, and then the geologist will go and he will tell to the civil engineer whether the support is required or not required before taking a next blast. Because if it is, now we have one face. Face means the front portion is called as the face, and we have two walls, and we have a crown. The walls condition will be different, or then the roof condition will be different, face conditions should be different. So face has to be mapped, all the data, whatever I am telling, all the data of the face has to be collected as 1:100, means 1 centimeter is equal to 1 meter. And the wall cannot be 1:500. It cannot be 1:500. 1 centimeter is equal to 5 meter. And according to the same thing, the crown. So this is a sequence that how we are collecting this thing. And the very important parameter is this is the adjustment. Suppose my tunnel is going like this, and my unfavorable feature is along this alignment. Can we change the alignment so that during the excavation you will have a less problem? And less problem means definitely the support system will be less. So what I am telling, these all sort of the thing, the background is the control blasting. In the morning you see the control. If you are doing the control blasting means my support will be less. Why the support will be less? Because my damage zone will be less. So these all are interrelated. So this thing, when we are fixing this, then we'll discuss this. Being a consultant, our organization is the consulting organization. We'll discuss with the project authority. Can we change this alignment? Suppose we'll go along this alignment, you are going to have a less sort of the problem. So this all should be collected from the side. So this some sort of the chart I have shown you that how it is rating actually, this rating, UCS rating, how it will be, RQD rating, spacing of discontinuity, and the mean spacing and the RQD, how it is rating. And this is the simple meaning. Means suppose my rock is very good quality. Suppose my rock is very good quality, means my stand of time will be more. My stand of time will be more, so my progress, I will get a more progress. Means without support, I can have a many blast, I can have a many excavation without support also. As my rock mass condition is degrading, the support system will be more, my pull will be less, because this is a cycle. This is a cycle. So how to increase this cycle? So, and again, this thing, in the preliminary design, when the preliminary, you are going for the preliminary design and you are having the exact this thing, rock mass classification, then you will have the average stand of time for the different rock mass class. On the bottom it is given, and then you will have the strength characteristics also. In addition to that one, this the support for the different diameter of the tunnel can be recommended based on the rock mass classification. So many organization in the world, including many organization in India also, they are using this classification only for the making their underground excavation, underground this thing. And this is the standard of time is given, that how you correlate, how you tell that this the most important part. Now you see how important it is. The owner of the project is telling to me, give me in writing, that you are permitting the somebody to take a next blast without support. You give me in writing that it is not going to fall. So how you go to this thing that the rock mass is not going to damage, it is not going to fall. We have a well established and more important part, well established classification. In addition to that one, your engineering judgment is very important, very important. When I am talking about this thing, you see, I am having the face, I am for underground, I am having the roof, I am having the left wall, I am having the right wall. Suppose two set of the discontinuities are there and they are inclining towards one direction. Suppose it is very favorable for this wall, it must be very unfavorable for this wall. It cannot be favorable for all the four sides. Somewhere it will be very unfavorable. So this stand of time is, you just remember this word, because in future your project authority, they will ask you, being an engineer, that what is the stand of time of my tunnel. So that from this thing, from the RMR values, you will come to know that one. And RMR, in addition to that one, it can be the word all across the world people are using the empirical equation that can be used for the estimation of the modulus of the deformation. That is a very important parameter from RQD, from Q, and from RMR. We can calculate the modulus of the deformation, which is very, very important parameter for the designing of the support and is being used for the design. We are not using anywhere for the classification. This will be used, but this will be very good, important parameter, because you know the rock mass condition, how your rock is going to behave at the time of the excavation. Whatever the data we are collecting the data before the excavation, not during the excavation. And what you are projecting? You are projecting the things, you are projecting the data for during the construction of the project. And this is the history of the Q system, very important classification. And in your Telangana, for the Palamuru Ranga Reddy lift irrigation, for the Kaleshwaram lift irrigation, for the Devadula lift irrigation. Now Devadula, you have the world longest tunnel. You people can go and see in the Warangal area, 54 kilometer length of the tunnel. That is the world longest tunnel for any sort of the irrigation purpose. Again, we have made a two shaft, one for the powerhouse and another for the storage of the water. They are the world deepest shaft, open this thing excavation. So you people, because it is in the Warangal only, and if you go into the Siddipet area, the 56-meter world largest diameter surge pool, this shaft, we have made it using these classifications. So this is the some sort of the beauty of this classification. And what I am telling earlier, the only the examples we are taking from the Scandinavia countries and mainly the Norway. Now we have a lot of the example from the India also, because this group, this NGI, in the morning, our previous speaker, Dr. Jhasa, was told regarding this NGI, not only geophysics, but they are very good in this one also. So there's a continuous research, and if you Google it, you will get a free document is available, published in 2015 regarding the rock mass classification using the Q. If you Google that one, you can download. That is around 60 pages document, very important document. So, and this is actually we have three questions they have proposed, and in the three questions we have a 6 parameter. Now the first 3 parameter they are related to the block size. Now next 2 is the related to the shear strength, and the third one is the active stresses. So these are the, suppose if the RQD will increase, your rock mass will increase. The top parameter, numerator will increase, the values will increase, your rock mass will increase, your rock mass will improve. But in case of the denominator, that value will increase, your rock mass will decrease. So this is the very important. You see, the physical parameter of the rock mass are taken into the consideration. That is the first questions. Second one is active stresses. What are the active stresses? That is the C and phi. If you go in detail, because only I am touching the rock mass classification here. So this, the JR upon J, JR and upon J is the active stresses. And if you touch upon this, because this water is a big issue, big problem, and stress reduction factor, always the question will come from the new our new engineers or the new engineering geologists. So how to determine this SRF? It is very difficult to determine. It is not difficult to determine, I tell you. If you go, you see, it is a continuous process. It is a continuous process. This vertical stresses can be estimated. It is a world established norm. And from that one, we have a number of the case studies, or for the in situ stresses, our organization, RRM, is the world leading organization. In a different sector, we have a number of the case studies. And suppose Telangana, suppose if we have a study at the X point, we have the Y point. Suppose you are not having the study at the center of this thing, you can develop something of the empirical relation. But my sincere suggestion is, for finalization of the sort of the longest axis of the cavity without in situ stresses, it cannot be. We should not take a decision, final call. So this is not a very sort of the big issue, and these are the how this it is characterized. In case of the RMR, the values are ranging from 100 to 0 to 100. But in case of the Q, the values are ranging from 0.001 to 1000. That is the difference between the RMR and Q. And this based on the this thing, it will fall again the exceptionally poor to the exceptionally good. How we can from the joint volume, suppose this is how to calculate JB and how it can be converted into the RQD. This table is given from the question. Again, many times the people are asking this question: Can we characterize the rock mass using the borehole logs? This is the borehole log. This box. This is a box for the borehole log. Yes, the answer is yes, we can characterize this thing. And again, this thing, how this one parameter regarding the JN and JN, how why this JN, how you can go exactly. Actually, if you have some idea about the stereographic projection, that is very much required. It is a very frustrating job, I tell you. My honorable director told you in the morning, our job is not a white collar job. Why it is not a white collar job? Because lot of the data, taking a final decision again for the underground at the at the 5 meter. For the nuclear power, 60 centimeter. People are asking how you are collecting the data. You see, so if you go with this thing, exactly, if you have a stereographic projection of your joint set data, pole, you can have a pole unlimited number, 200, 400, 500. But and again, why this seniority has to be maintained and this thing, engineering judgment, we cannot take more than 3 joint set in our analysis. It should be very clear that more than 3 set, if you are taking, then somewhere we are making a compromise with the support, or the support, if you are making a compromise with the support, means we are making a compromise with the safety or the life of the structure. So which parameter you should take into the consideration, and which parameter, which joint set you should not take into the consideration, that has to be decided before taking a final call this thing. So that is a brainstorming sort of the thing within a group. We have a group of say 4 or 5 people. So simply we cannot say 3 set, 4 set, 5 set. No, it cannot be like that. Because this is again in case of this parameter. This is a denominator parameter. You increase the value, my rock mass will fall. My rock mass will fall. Again, we have to go for the extra support, which is not required. Ultimately, aim should be the recommendation of the optimum support system. An optimum support system will come only when we have a actual field data. Because again, the safety and life of the project cannot be compromised. So this is how this look actually, 1 set, 2 set, 3 set, how you can define. Again, this is a surface, big science itself. Joint surface roughness. Again, this one scientist Barton has proposed, and the one Indian scientist along with the Barton, Chobe and Barton. Worldwide this is being used because this JR and J you can convert into the shear strength parameter. And the shear strength parameter from where you are getting, either we have to go for the triaxial shear test or direct shear test. How many projects we are going for the triaxial shear test? We are not getting. So this is the parameter, very important parameter. We should have this. And how you can, you see, this is very important. Please go through that book that is already available and see this one, that how this one, the stabbed, undulating, planar, it should look like. It is a physical observation. So this is a some sort of this thing, that how you'll come to know that this thing. And again, this is the groundwater condition. This physical observations are also given here. Again, we can measure this thing also. A different pattern is there. For tunnel, how we can measure, this is the different pattern is there. So the problem will be there, then how to give a rating for the groundwater condition. It should not be more, it should not be less. Okay. Then the stress reduction factor, as I told you, 4 conditions are there. So the 4 condition, out of the 4 condition, only the engineers will face the problem in the competent rock mass is there. In the rest of the condition, the engineer or the geologist will not face the problem. So this is some sort of the ratings are given. So I will not take much time. This is again the important parameter, how we have expectation that if not supported properly, we are going to have a daylight. Means the tunnel will collapse completely. So this is some sort of this thing, that how much area has to be protected. Not only that area, but how much area has to be protected. This it is defined in this this thing, and this is the means which type our stresses, how it will behave for the slope and this thing. And as I told you, whether the rock mass can be characterized from the surface exposure, yes we can. From the tunnel, yes we can. From the borehole and from the exposure, all this thing we can have this thing. And this GSI, I will not take much time, but GSI is a one parameter which is being, this is a graph. From this graph, this is a matrix of the 6 into 5 parameter. On your left vertical, it is a this is the 5 parameter, 6 parameter. On your left means interblocking and the surface condition, 5 parameter. So 6 into 5 matrix, if you go with this thing, you can characterize and you can assign this thing. And this is the RMI is the new classification, Palmerstone, proposed by the Palmerstone. But this is so far we are not using this thing because of the less case studies. And this is the sum of the case studies, as I told you. From the borehole, we are characterizing on your left, this is the log of the borehole. We are characterizing the rock mass. On your right, this is the tunnel actually. the tunnel again, how we are characterizing and making a geological and geotechnical. This is an example of the foundation of the nuclear reactor, that how we are mapping this, as I told you, that what should be the scale for this thing. It is the foundation of the pump house. This is the as I told you, 56 meter dia for the Kaleshwaram lift irrigation package 5. You can see, you can go and see, and how you see the problem, the foundation we will be there. Our colleague is standing, so that is the size of the weak zone. That is the size of the weak zone. At this particular site was stopped for more than 2 years in our Karnataka, and after the interference of the High Court, our Karnataka High Court, this work was again awarded, and that this foundation was treated. So after detailed investigation, yes, it can be done, and this is an example of the after this all this thing exercise, we call it as the as-built map. This is the example of the Mangalore underground crude oil projects. For all the 3 underground crude oil project, our involvement was there, and finally this all geology, geotechnical, whatever you can see, it is not readable, but what I am telling, suppose every this thing, which type of the supports are given, what is the thickness of circuit, what is the length of the rock board, spacing of the rock board, where my instrument is there, which type of the instrument is there, all the type of this thing should be detailed in a one map. So my planner and the reviewer will see only one sheet, that is a as-built map. So our organization is doing this exercise also after the completion of the work. Thank you so much. You have a question, you can put up in a chat box, I think. So we'll reply later on because of the shortage of time. You can put up in a chat box. Thank you so much.
Thank you so much, sir, for briefing our students about engineering rock mass classifications for underground structures and foundations. Now I invite Professor T. Madhavi, convener of this workshop, to present a memento to Dr. A.K. Naitanya. And I request Dr. C.H. Akhilesh to join. I deem it my privilege to introduce our esteemed guest, Dr. Shiva Prasad BNV. Dr. Shiva Prasad BNV is a graduate in mining engineering with postgraduate and doctoral degree in mining from IIT ISM, Dhanbad. He is a scientist C in the numerical modeling department of NIRM. His expertise includes the application of rock mechanics principles to solve wide range of industrial problems using numerical modeling techniques, and so far he has completed over 50 industry-sponsored projects. His work area include mining, tunneling, hydropower, infrastructure, and irrigation sectors. He has rich experience in lead, zinc, gold, copper, iron ore, uranium, aluminium, and coal mining. During his tenure at NIRM, he was on deputation to Punat Sangchu 2 hydroelectric project, Bhutan, for 4 years. He has visited Bhutan, South Korea, Singapore, and Austria on numerous assignments. He is life member of the Mining Engineers Association of India and a member of the Institution of Engineers India. Prior to joining NIRM, Dr. Prasad worked at Zawar Mines HZL in the Mining and Rock Mechanics Department, contributing to mine transformation, VIS mining, rock mechanics, and geotechnical aspects. He is certified with a second-class mine manager certificate of competency in metalliferous mines. Thank you. Now, I request Dr. BNV Shivaprasad to give his talk on monitoring underground excavation, VIS, AVIS mining and tunneling. Over to you, sir.
Thank you, madam. Okay. Good evening, friends. Hello, everyone. I would like to seek your attention, please. So, with yesterday's rain, since it's raining yesterday, so we have seen that your energy levels also have come down. Is it so? Yes. So, hopefully, from since today morning, we have seen so many lectures. So, which might be somewhat interesting, somewhat boring, somewhat we will be seeing why we are sitting here. Do we really need these topics in our life? Whether we will be going to such project sites or not. So, these all questions might be there in your mind, and instead, even some of you guys might be chit-chatting around these projects also. But the physical aspects of these projects and the real importance of our careers, we'll see that in our career how we move ahead in our path, in our career path, we see that where we land up or in which project we will be contributing, we never know. So being a mining engineer, I have got an exposure to so many various fields after coming to NIRM. So this has given me a completely new perspective of looking into rock engineering. So which we will be sharing in these lectures. And I hope since morning we have seen various topics covering and giving a glimpse of how a rock engineer works in various fields, like contributing his best to the development of nation. So this is the lecture series which is organized as a part of Azadi ka Amrit Mahotsav. In this sense, we are trying to raise awareness amongst the students that the branch which you are studying, I want to know how many are from civil engineering background here. Mining, rocks. So mechanical, electrical, aeronautical, and others. Great. So I'm happy to see so many hands and so many students still actively participating in these conversations. So today I'll be presenting something about monitoring underground excavations. So this is as old as Stone Age, where people used to use rocks to dig rock, and to the latest in the 21st century, we can see the use of artificial intelligence. CS guys also has a lot of scope in rock engineering. Various excavation dominant sectors includes mining, hydropower, traffic, urban infrastructure, nuclear and petroleum. Coming to excavation methods, we can see that excavation is a process of digging into earth. The place where we dig, be it surface or underground, it deciphers the type of method of excavation. Giving you a glimpse of underground excavations, how it looks like. So being mining engineers, they are more or less exposed to mining environment, where we see a 3x3 drive, where a scoop ram or LHD is used to load the material and transport the broken ore, and a drive where the support is installed here. Here we can see hundreds of meter long cavern is excavated underground, which people will not have even a slight sense that where we are standing, 100 meter beneath us can be a cavern also. So what we see is a magnificent underground structure, but what exactly is going on behind that is a matter of real concern. So we can see several tunnels, some infrastructure projects for pipelines, sewage, etc. And you won't believe some of the hockey stadiums, underground hotels, research laboratories are also all converted to underground rather than keeping them on surface. Coming to excavations in mining sector, India has a huge potential, as my preceding speakers have already spoken a lot about it. And coming to stats, in the year 2021 and 22, about 18 gigatons of mineral production has been done worldwide, out of which India has contributed about 7%, which is tuning to a whooping amount of about 1.9 lakh crores. Coming to hydropower sectors, since there are many civil and mechanical engineers as well, we can see that CEA, Central Electricity Authority of India, has identified a electricity generation, hydropower generation capacity of about 1.45 lakh megawatt, out of which about 92,000 is yet to be taken up for construction. So we can see that what is the scope for civil engineers and mechanical engineers and many more other fields, allied rock engineering experts to come in the future. To give a glimpse of what is the scale of excavations required for a hydropower project, these requires, as we all have seen in the previous presentations, that these requires a huge quantum. That what is that huge? That huge quantum means about 1 crore meter cube of volume for one project. Just since we can see many ladies and gentlemen over here, we are very much fond of gold. So in order to get 1 tula or 1 gram of gold, we are just paying some money and we are getting gold very easily. Gold coin or gold bead, gold biscuit or whatever ornament you want, you will get it. But do you know, in order to get that 1 gram, we need to blast over a ton of material. When we blast some tons of rock containing gold mineral in it, then we get 1 gram of gold. That we easily buy with 6,000, 7,000 and get it. But the pain a mining engineer or a rock engineer takes in extracting that gold is the real engineering. It's not a matter of gold, it's a matter of every material that each and every engineer uses to develop something that is coming from mining engineering. So, somehow or other, each and every branch has a role to play when it comes to rock engineering. So therefore, we need to understand what is its mechanics. So it is basically a theoretical and applied science of understanding the mechanical behavior when we apply some forces. So we see that already Dr. Naithani has explained about the rock mass classification and characterizations. So we see when a rock material is seen and we excavate in that material, we find somewhat this kind of situations. Whereas when it is coming to rock mass, the presence of discontinuities makes it unique, and this differentiates it from rock, and we encounter somewhat this kind of scenario. So therefore, we can see that these are the joints and there are certain blocks formed over here. These are the potential discontinuous wedges which are likely to fail, and this we need to prevent so as to have a stable underground excavations. A poor understanding of rock mechanics can result in several catastrophic failures. Here we can see a wedge failure in an underground mining. There is a shear failure where the rock material has flown into the gallery or the excavations. The flow of sheared material, just like soil like material, and the presence of water has indicated a shearing of this material and washing away of the weak zone, and the support whatever has been installed is exposed now, so leading to a unsafe condition. And sometimes we see that if despite our best efforts in supporting the rock mass conditions, we see that this also will not stand against the nature, that means like the forces of nature. In one of the hydropower cavern, we can see that there was excavation going on and about 1 lakh cubic meter of volume of muck has flown into the cavern, and then this is 30-meter high cavern. We can see a 10-storied building like muck is in front of us, and we have nothing to do with it. We have to deal with it and move ahead with underground excavations. So here, this is where there were many casualties, loss of life, loss of property, and also the project was stopped for almost 3 to 4 years, where there were thousands of crores of Government of India's money which was locked up, and then there was loss occurring, and this interest was growing like anything. So sometimes these failures can result in subsidence also and lead up to surface and result in massive collapses and then also depressions in the surface area. Even this can be possible in the hardest of the hardest rocks. So as a rock engineer, there are some factors we need to consider in our design so as to prevent such kind of failures to occur. So the first and foremost factor is in situ stress. As we all know that the formation of earth itself is a big mystery, but the fact is at every location on the earth, and in the earth it is having a history point in it. That is nothing but a formational stress. So we have certain stress component in it, and then this can be due to surface topography, tectonic movements, overburden, and different kinds of factors are involved in it to give a stress at a point. And basically these are defined by principal and shear components that we already that we also study in our solid mechanics, or be it soil mechanics or engineering mechanics. The field may be different, but the concept is same. There are 3 principal stresses and there are 6 shear stresses. That's it. The application will change, that's all. So the most commonly used method for determining such in situ stress is hydraulic fracturing, where we try to drill a borehole and determine the core and determine the test zones where we insert the packers. This is the team of NIRM, Geotechnical Engineering Department, who is conducting hydrofracture test in a large underground cavern, and then we insert the packer and then inflate it and see that what is the pressure and the drop, and the pressure time history is recorded, and we find what is the stress at which the rock is cracking, and we determine the orientation, and finally we determine what direction and what is the magnitude of that stress. So following that, we result or we design our excavations, orientation, size, shape, etc. Second important parameter of any material is that since we are dealing with material and considering rock as a material, we need to know its strength and deformation properties. So here, based on the presence of joints, we can see that there could be a numerous situations in front of us. If there are no joints, we would be encountering something intact rock scenario. If there would be single joints, such kind of rock mass conditions. If there would be 2 joints, we can see such kind of thing. And there is, if it is heavily jointed, we can see just like a net. The rock mass can be so fractured that we have to deal with it. So we need to have its compressive strength, uniaxial, be it triaxial, confined strength, be it cohesion, friction, shear parameters, and also some kind of deformation parameters like elastic modulus, shear modulus, we need to know it. Testing in laboratory, like the way we deal with the civil engineering material or any kind of steel, ISMB sections or ISHB sections, we need to determine its tensile strength, and then we need to determine its deformation, Young's modulus, right? So in the similar way, the rock also is determined in the form of core, and then it is tested for determining its uniaxial compressive strength, also the tensile strength, Brazilian tensile strength, the shear properties, and also the dynamic, that is ultrasonic velocities, that is P wave and S wave velocities, which were previously discussed in the previous lectures. Second one is like rock mass structure. Since we are dealing with rock mass and not rock in engineering projects, we have to characterize the rock mass. So this has been elaborately discussed in the previous lecture, where we are completely characterizing based on the joints properties, orientation, their stand-up time, etc. And then for this, we use a kind of Brunton compass, and we see that on encountering a rock mass, we need to identify what are the different joints and how do they look like when they are encountered with different sets of joints over here. And these are plotted on a stereo net, and then we see that this is the cavern, transformer hall cavern, and then when these structures or the joints are plotted on this cavern, this looks somewhat like this. And here we can see there was overbreak sections which are plotted over it, and then this is showing that there was a shear zone which is a weakness plane, and here there was a maximum overbreak section. So this all infers that the hydrological conditions and other parameters play a huge role in determining the stability of the excavations. So under excavation design, we need to see the shape and profile of excavations, because once we excavate, we are actually disturbing the natural in situ stress present in that medium, and then the stress along the periphery of the excavation surface that will get redistributed in the abutments. Just the way we design this auditorium, civil engineers must be well versed with this terminologies, that when we design such kind of space or a floor, we design the roof, the slab or the floor, the pillars, the columns, everything. So depending on their strength, we see that whatever stresses coming on over the first floor or the above floors will be transmitted to its abutting pillars. So the similar way, the in situ stress also gets redistributed around the excavation periphery, and this is usually determined by using numerical modeling tools. Excavation design. As we have seen in the first lecture in the blasting, where we have seen that here this is one of the typical case where the cavern was excavated and there was a massive collapse of about 14 meters. And the means like the scale of overbreak actually hints that when there is a lack of proper blast design, this could be the results. So this was observed in the project site, and with the intervention of rock blasting department of NIRM, we could see that this overbreak could be limited to about 0.5 meters, so which is less than 15% of the total excavated zone. Especially in the rock mass, when we cut, it is not like a cake that we cut a slice and have it nicely, and then we can have a clean cut. It's not like a cake. So when we deal with rock mass, so there will be like undulated surfaces which we need to deal with it, and then we have to see that we must not be breaking over a certain designated line or excavation design. So we can see that there is a smooth, after the intervention of rock blasting department, we could see a smooth line of excavations well executed at the project sites. Also, we need to see the cause and effect depending on the sequence of excavations. So as we go into mining sector, we go and approach through crosscut, and then we carry out a blast, and then we progress in both the direction, and until and unless the slice is mined out, we keep on carrying. So here excavation in the heading portion, and then this is benching portion. We go ahead, if there is a very weak rock mass, we excavate it in two portions, that is half in the heading as a heading and half as the benching portion. So here we carry out blasting, and we see that we advance in this direction so as to make a void by using drilling and blasting. As we can see that this is the only method which can be adapted in very soft to very hard rock conditions. So we use it more prominently in any kind of engineering projects that we see. So here we use a drill jumbo, and then we drill the holes, we charge it using explosives, and then we blast it. So when we blast it, several fragments, as we have seen in the morning session, we have seen certain videos where these fragments will be thrown away in the free phase direction, and then the fumes are ventilated and de-aired, and then the blasted muck is removed or loaded and hauled to a different loading point using an LHD, and then we scale the loose rock mass over the excavations, and then we spray shotcrete if required, and then we support the structure or the underground excavation. So all these steps or creation of an underground excavation will result in accumulation of stress in the pillars, where we can see that the more the excavation, the higher the stress concentration in the stress pillars. So in order to determine what is the stress in such kind of rock, we use many kind of numerical tools or numerical modeling methods, be it continuum or discontinuum. Depending on the type of discontinuities we need to deal with, we will be classifying it as continuum and discontinuum models. So once we know the extent of damage, then we go ahead with the designing of rock support. So where we see that there can be two schools of thought. We can just imagine that who needs to put a rock bolt when we are going to mine out and go away from here. And some may think, why to take any chance when we are going to work here? So we have to somehow judiciously strike a balance between these two schools of thoughts and come out with a proper judicious support design, so that any discharged or any dislocated rock blocks have to be retained in its original position. And there are several systems to withhold this kind of detached rock blocks, such as rock support and reinforcement in the form of rock bolts and cable bolts. It's just like the way we stitch or bind our book. We have our notebook and we bind it by using a needle and a thread. In the similar way, we try to bind different layers of rock using such kind of rock bolts and cable anchors. So we spray shotcrete so that wherever there was minute or fractured material, this can be withheld at its own place, and also it gives a cosmetic look. So basically monitoring. So once everything is done, we need to monitor. What exactly do we need to monitor is the question that we need to ask oneself. That unlike engineering material like steel or concrete, rock material is something different, where we have a lot of uncertainties, and we need to monitor various engineering parameters such as displacement, loads, stresses, strain, seepage, like pore pressures, temperature, uplift, seismicity, and so on. But ultimately, all these parameters boils down into two parameters, that is displacements or deformations and loads. But how do we measure? So this is through an instrumentation. So a successful instrumentation program starts by questioning that if we are putting an instrument there, what is the purpose of it and what is that we are going to get from it? So which parameter is we are going to obtain, and then what is that, what the value will intend. As an engineer or a designer, we need to know that if the value is such and such, so what step we need to take. So that instrumentation plan is the basic requirement of any excavation project, so that its performance of such kind of structures can be monitored. So this basically has a sensor in it which responds to the changes to the variable being monitored. So if we apply some load somewhere, some deformation occurs. So that deformation is the parameter which the sensor detects. And a transmitter transmits the sensor output to the readout location, and a processor usually processes the data and then acquires the data in the data acquisition system. There could be several technology over a period of time, various mechanical, optical, hydraulic, pneumatic, and electrical, like vibrating wire sensors have also been developed, where in a vibrating wire sensor, a wire is plugged magnetically, and this sensor is the output signal is measured by using a data logger, and the frequency is displayed on the data unit. Various instruments that we may be using for monitoring various parameters includes some kind of extensometers, pressure cells, piezometers, magnetic ring extensometers, the stress cells, concrete stress cells, piezometers, load cells, and so on. So when it is coming to tunnel instrumentation, we have seen a underground metro stations development, like where 30 meters or 50 meters down from the major working roads are being excavated. In such scenarios also, we see that various instruments are actually installed, such as inclinometers and the monitoring the loads, extensometers, deformations, and along the beams also we monitor the strains in the beams and columns by using strain gauges. So all these instruments will help us in determining the value. It again depends upon the designer or the person who is reading the data, that how exactly it means to us. So the key monitoring applications in mines, in underground mines, include settlement like surface subsidence, deformations, loads, displacements, and we use certain instruments like extensometer, convergence meters, stress meters, etc. And similarly, in open pit mines, we see the deformation around the excavations, stability of the pit walls, groundwater pressures, excavation floor heaves, and in instrumentation we use inclinometers, piezometers, crack meters, etc. And in mines, similarly, tailing dams are also there. In tunnels especially, we monitor the convergence and the displacements and floor heaving using various instruments. And then finally we use the data loggers to acquire the data, and data is analyzed, because we are, after all, we are in the era of artificial intelligence and machine learning and deep learning. So we always try to acquire data, but ultimately what is that data trying to speak to us or convey to us? That's a big question mark, which needs to be addressed by the engineer who is actually designing the process. So this is a process of evaluating the data through analytics and statistics for discovering useful information that can aid in sound engineering judgment. So a case study from hydroelectric project from Bhutan. Here I would be saying that there would be a runoff river scheme where the river water is diverted through a headrise tunnel, and from there will be surge shaft, and then through butterfly wall chamber the water falls down 200 meters, and then the water flows into the cavern. This is a machine hall cavern where we can see there are large turbines which are fitted in it, and the water is used to run these turbines, rotate these turbines, and the generator fitted over it will generate the electricity which we are using it comfortably in Hyderabad. So all this power is generated, and then for this excavations we require rock engineers. So in this project there was a massive collapse which I was mentioning in the previous slide, and then these were the 3 caverns, parallel caverns. How to monitor these caverns in underground? So where the excavation height is about 55 meters, and we can see that about the length is about 314 meters. So we can see that it's just like a football stadium. So we can see that these are different instrumented sections. This is an instrumented section where different instruments like MPBX, displacement sensors, load cells, instrumented rock bolts, and piezometers are all installed in an array. And then this is the shear zone across which the failure has taken place. And then we can see that this entire health of this entire caverns were monitored continuously. And interestingly, this data has not been means like gone waste, because this has provided the areas of critical reaches where we could see the maximum dilation of about 32 mm. And these locations, we could see that while remedial measures implementing, we could see about 719 bags of concrete or cement has been pumped into just one single borehole, where at other locations where the instruments have not indicated any critical points, there hardly 4 to 6 bags was consumed. So this implies that instrumentation has a very huge role to indicate the critical reaches. And then we have monitored the structural health between the structure, that is pillar between the two caverns, and we could identify what is the damage zone, and we have designed the remedial measures accordingly. Also, this detachment can be physically seen at site in the form of bulging, cracking in shotcrete, etc. Sometimes this cavity can be as huge as 45 meters, 90 meters, which can be 30-stored building. So we can imagine that what could be the way, or we need to monitor these kind of cavities, because in underground caverns or underground excavations, once these cavities are encountered, we have to deal with it. Otherwise, the project is stuck. There are several instances across the globe that where the projects are halted and stopped because of such kind of cavities, and we are unable to deal with it. So this is also a very important aspect in kind of underground excavations, where a cavity monitoring system, this was inserted by using a borehole up to a depth of 150 meters, and then the cavity above the downstream search chamber. This is a cavern, and this was monitored by using a cavity monitoring system. This is the system, which is a LiDAR sensor. And then we drop down this to up to a depth of 150 meters, and then determine the shape and size of the volume of this cavity. And then when we are filling this cavity also, this cavity monitoring system is also used to see that what is the volume of concrete that we have poured into it, and then what is the direction of flow of concrete. Each and everything we can capture it. And then the volumetric analysis was done for filling this cavity also. This is the cavern, and then we can see the extent of failure. This is about 96 meters from the actual designed level of excavation. So here we have designed an indigenous setup of instrumentation network to install inside the muck. And then here, because these instruments are also not suitable for each and every case, that we got an instrument and we can fix it anywhere and we'll get it all sorts of data. This is not so. If a project demands certain data, then we need to devise our instrumentation in such a way that we acquire such data. So this is one such attempt made in that project, where the indigenous product was developed using load cell and borehole stress meter, where we get the loads and stresses as well, and also the strains in this rock bolt was can be determined, and this was drilled up to a depth of 30 meters inside the muck, and then these were installed. And we can see this is the life of a rock engineer. The blue collar job, so called, hard hat job, so called. It's not a white collar job, but yes, if we develop a passion in this field, so we definitely feel more and more interesting to do such kind of activities, because this is the real data that we are generating, and we are not generating the data through some algorithm or some kind of random number generator, some kind of sequence. It's not like that. It's the real data that we are obtaining from the field, which will be utilized by a computer science engineer or a AI ML expert to derive or to predict the future or the behavior of this material. This is another interesting tunnel where excavation was made in very fair rock mass to poor to very poor rock mass. Excavation was going on as it is in the heading and benching way. And then we could see that as the excavation was going on, we have monitored by using MPBX and load cells. And there was twisting of ribs. These are ISMB ribs. Civil engineers can better understand this. So these are ISMB sections, ISMB 250 and 300 sections, which were twisted. That means the stresses or the loads coming on at this location are much higher than its capacity. So therefore, when monitoring through instrumentation, we could see that there was no instrumentation rise, but as soon as the excavation was carried out in very poor rock mass conditions, suddenly there was a spike. So this has given an indication that there was a some collapse or some kind of distress activity which was going on behind what we cannot see by this naked eye. So this is what is indicated by this instrument, and suddenly the excavation was stopped and the excavation methodology was altered so that these deformations were controlled, and then later on excavations were carried out very comfortably. These were certain critical locations where the instruments were installed. And also the excavation, sometimes we have a very complicated excavations, like we have only 7 meters of block or the pillar between two caverns. Again, this was made possible with the help of control blast design done by our blasting engineering department of NIRM. And instrumentation also, the installation of instrumentation could be made possible to be installed at a gap of about 0.5 meters. Again, this credit goes to again blasting department, so as to design their blasts in such a way that they did not damage our instruments. So again, this is again also has served us in a lot of control way of manner. We could able to get a lot of quite informative data. And this is the condition where tunneling aspects are seen. The water is continuously pouring out. In such conditions also our instruments will survive if we plan our instrumentations correctly and then see that our excavations are also monitored continuously. Some kind of cable anchor load cells are installed in such project, and then this is the cable anchor load cell instrument, and the stressing equipment is shown here. And then this is the calibration process. So if we stress the load cell up to 150 tons or 100 tons capacity, we have our load cell also, the instrument, which will also tell us that whether the loading has been done till 150 tons or not. So this exercise is also carried out for each stressing of anchor, and also some kind of prism targets are used to monitor three-dimensional deformations. And numerical modeling, as mentioned, so this actually gives us a picture that how the caverns behave when certain collapse occurs, to what extent it has its failure or yielding limit or the stresses redistribution. This all things can be evaluated or assessed only by the help of numerical modeling. So some works can also be done in was also done in drifts of dam, where there were installed MPBX, that is magnetic ring MPBX, and also some temperature sensors and strain gauges, and also stress meters, concrete stress meters. And this was one another development that was done by NIRM, that is a three-dimensional strain gauge meter. So this was developed only to serve the purpose of monitoring in concrete cells. This is certain different drilling locations where we see different rock mass conditions encountered, some surface subsidence applications in mining, blast vibration monitoring, and then numerical modeling, that is subsidence modeling, etc. And then we can see that when we design an underground mine, we could see the skeleton of mine could be somewhat like this. And then when we backfill it, this will be somewhat like this. So as a mining engineer, we need to design various mining methods, and then we need to conduct certain failure analysis as well. So ultimately, all the attempts goes into ground control management, and then these all are actually deliberated with the students and the engineers and the professionals from rock engineering fraternity in the form of training and site visits, and then following India and abroad as well. And then, thank you. I guess everyone is eagerly waiting for this moment, right? Okay. This.
Thank you so much, sir, for your encouraging words to our participants. Now I request Professor V.R. Shastri, Director, GITAM School of Technology, to present the memento to our esteemed guest, Dr. B.N.V. Shivaprasad, Scientist, Numerical Modeling Department, NIRM, Bangalore. I request Professor T. Madhavi, convener of this program, to join him.
ऑन है मैं देख रहा हूँ हाँ 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 आप लोग स्टार्टिंग से लेके वो शेयर होना है ना, शेयर नहीं हुआ अभी।
लेकिन वो उधर ये है ना, रुको रुको अभी साथ में करो शेयर।
शेयर करिए ना, स्क्रीन को शेयर करिए। हाँ, उसके बाद फिर
सर प्रोजेक्टर को ऑन करना ही है, प्रोजेक्टर को ऑन करना ही అంటే అది ఆన్ చేయాలి కదండి, ప్రొజెక్టర్ ఆన్ చేయాలి. పట్టుకున్న ప్లేస్
This is the 1-minute AV based on our today's session. I request Professor V.R. Shastri, Director, GITAM School of Technology, Hyderabad, to grace the dais. I request Dr. C.H. Akhilesh, HOD, Department of Civil Engineering, to grace the dais. I welcome Dr. P.C. Jha, Scientist and Head Engineering, Geophysics, Department, NIRM, Bangalore, to grace the dais. I welcome Dr. H.S. Venkatesh, Director, NIRM Bangalore, to grace the dais. Now I request Professor V.R. Shastri, Director, GITAM School of Technology, to address the gathering.
Friends, I think you are the best judges. Audience here, I don't want to take much of your time now. I think every one of you are eagerly waiting to catch the bus, I know, including faculty as well. I only have one word, one sentence to say. I think you all must have enjoyed the lectures of NRM, and all of you must have got some knowledge about rock engineering and progress of the nation. And I assure you that we'll have many such programs in the future days to come, so that our GITAM University becomes more vibrant and dynamic, and our name is known everywhere in the country, including the power corridors of New Delhi as well. That's my aim, and I'm very sure with all your cooperation and help, we'll be able to achieve it, to take our university to new pedestals in the country and at the international level as well. And I profusely thank once again Dr. Venkatesh and his team members, led by Dr. Jha and Dr. Naithani, who have been my very, very personal close friends for more than 2.5 decades or so. And every one of you for making this program a grand success. Thank you very much.
Thank you, sir. Now I request Dr. P.C. Jha, Scientist and Head Engineering, Geophysics Department, NIRM Bangalore, to address the gathering.
Yeah, I have been carrying out this program since last 6 months, and we have come all the way to GITAM today. And we were just apprehensive how it will be. And today, after seeing the feedback and the list of participants, we have more than 1,600 registrations so far. And 22 colleges are there online. So this is one of the highest response we got so far. From March, we are organizing this program, and next month it will conclude. And what we saw is this is a program for the students. If the students show interest, our purpose is solved. We are just propagating the message, what is the role of rock engineering in nation building, through our case studies. And what we could see, the response is very good, and that gives me the satisfaction. What we have been doing is nice. And we seek further support from you, and we will keep coming whenever there is a requirement. Thank you for your support.
Thank you, sir. Now I request our today's chief guest, Dr. H.S. Venkatesh, Director, NIRM Bangalore, to address the gathering. Thank you, sir. Now I request Dr. C.H. Akhilesh, Head of the Department, Civil Engineering, to address the gathering.
Sir, I'll just take couple of minutes because there are some important, regarding the participation, I just want to make some kind of announcement here. So as rightly said by Dr. P.C. Jha, sir, we had around 1,645 registrations across the 3 campuses of GITAM and including 25 other institutions, where we have the offline participation of 61 students and 5 faculty members from Usmania, Methodist College and Reddy colleges. We are very thankful, to all the institutions, the faculty members, HODs, faculty coordinators, and the, my dear colleagues and faculty and students at GITAM as well for making this event in such a huge quantity in both online as well as offline mode. And I would also like to make a point that the Volga University from Ethiopia, some of the students also participated through the WebEx and live streaming, and some students from Shantanu University in China have also participated in this particular event, which really, brings the international level of participation in this event. And we are really thankful to the management of GITAM and the Honorable Provici Garu, Director Sir, and the entire team of NRM. So I really take this opportunity to thank each and every organizing committee member and all the expert speakers especially. We had a very wonderful web sessions in the entire day, and we really believe that most of the students and even the faculty members have got great learning curve, and definitely they'll look forward. Maybe even I have also got few topics in my mind, so I'll definitely would want to associate and Obviously, I believe most of other faculty colleagues also from the various disciplines, they are very interested in doing this kind of research as well as the consultancy. So thank you everyone. I'll not take much time. I just wanted to cover the concluding remarks, but I think it's just like because of shortage of time. And special thanks to the entire hospitality team again, and the transport team, all the committee members, organizing committee. A big round of applause for really making this event possible. And special mention to Varma Garu, who is a technical assistant from NIRM. I'm not able to see him, who has really worked hard. Thank you very much. And special thanks to Dr. Sudhakar Singha, who has made this 1.5 minute AV. He spent some 1 to 2 hours in making this video and wanted to play this. So thanks everyone. I really thank all of you for making this event a successful. We look forward to host many such events and see the participation from the other institutions as well. Thank you very much. So can we have some feedback from some of the students?
I request S. Sirisha from Osmania University to give her feedback.
Good evening to everyone, respected dignitaries and my friends. I am Sirisha from Osmania University pursuing MA in mining. One-day workshop on role of rock engineering in national building organized by GITAM Hyderabad in association with National Institute of Rock Mechanics NIRM Bangalore. It's a great honor to be a part of this one-day workshop. We have gained a lot of information on this one-day workshop. By the lecture series on rock mechanics, we are able to get a clarity and understand the role of rock engineering in nation building clearly. My heartful thanks to GITAM Hyderabad for conducting the workshop in association with NIRM Bangalore. Thank you.
Now I request B. Anush from Reddy College of Engineering to give his feedback.
Good evening to one and all. I am Anush of mining second year studying in Mallarand Engineering College. We are glad that we have been the part of this auspicious event for this lecture. The sirs have explained explained about great technologies and new advancements in these new upcoming days. We have studied the basics of this in our BTech standards. We had not gone through all this. They had said the difference between RQD, RMR and some of these. By this, we can encourage our India to greater heights. Thank you for giving this mission.
Thank you, Anush. Now I request N. Sai Dikshita Devi from Methodist College of Engineering to give her valuable feedback.
Good evening to the respected dignitaries, faculty members, coordinators, and all the participants. I am Sai Dikshita Devi of Civil Third Year from Methodist College of Engineering. It has been such an honor to be a part of this wonderful event. On behalf of our college, I would like to extend my heartfelt gratitude to NIRM, GITAM management, event coordinators, and organizers for the opportunity to be a part of such a remarkable event. The event was highly informative and knowledgeable. We gained a lot from this experience. The presentations and keynotes from speeches by speakers were exceptional quality. They covered a wide range of topics such as rock blasting, ground penetrating radar, rock mass classification, and also monitoring networking in mining and tunneling. They were informative and knowledgeable, which helped us to understand the importance and role of rock engineering in nation building. The insights of this event helped us to know the practical implementation of rock mechanics in developing the infrastructure of nation. And we also know how NIRM is resolving the issues related to the infrastructure in rock mechanics. Once again, I would like to personally thank all the speakers for enlightening us and GITAM management for their hospitality. Thank you.
Thank you, Dikshita. Now I request Ismail Nambirwa from GITAM School of Technology from the Department of Civil Engineering to give his valuable feedback.
Greetings, all the honored professors, coordinators, and everyone in here. Standing in front of you is Ishmael, a second-year civil engineering student in GITAM University, Hyderabad, representing the Civil Students Department. Firstly, I would like to thank Professor V.R. Shastri for enlightening us about the challenges faced in project planning and how to tackle them. I also want to thank Dr. H.S. Venkatesh for a good presentation about rock blasting. We also benefited from the engineering rock, mass classifications for underground structures, and monitoring underground excavations in mining and tunneling lectures by Dr. A.K. Naithani and Dr. B.N.V. Siva Prasad. We thank you, sir, for all those good lectures. In our syllabus, we only focus and go deep into soil mechanics, but we got an opportunity to go beyond. And I think as future civil engineers, it's a treasure to know more about rock engineering, which you did for us. On a scale of 10, I would give this workshop a 10 out of 10. On behalf of the students in here, I want to thank the organizers of this program. I also want to thank NIRM and all the professors who came through to teach us. A round of applause for this. Thank you.
Thank you, Ismail. Now I request everyone to rise for national anthem.
यमुना गंगा उज्जल जलधि तरंग तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
I request everyone to join us with for high tea.